I think the biggest disability that we have as human beings is unbelief. Everything starts with a vision, and a man without vision dies.
Here we are in 2022 and most of the games are multiplayer only. And of course, a legit question comes: is AI worth it anymore to learn and to use in your own games? And a spoiler, yes, it is worth it. But let's find out why. The main issue with all of these multiplayer only games is that they compete on one important resource. And that is not even money, it's actually time. And every player has limited time, 24 hours a day, 7 days a week, like everyone else. We haven't found yet a way how we can make much more time. But the thing is, once a player gets stuck in a particular game, they might not want to try a different one because their friends are all over in that game and already bought a lot of packs and items and stuff. So the move is really hard for them, only maybe if they get bored or they don't have someone to play with. This is called the sunken cost fallacy, and it's real. And this, of course, makes some winners like Fortnite and Minecraft, but also a lot of losers that you probably won't see because nobody talks about them. So this is one point, that a multiplayer game only might not be exactly what you're looking for. Let's say your multiplayer game is successful and it actually skyrockets. But then you get into other issues like making more servers available, lag mitigation, cheating problem, and much more. So you see, even if the multiplayer game is successful, you have a lot of things on your mind. But if your single player is successful, then just means that the sales go up and you don't have to waste more time in figuring out other types of issues. You can push some updates, but that's up to you. But the real problem with multiplayer only games that I have actually suffered it myself is called dead on arrival. And that means that when a game is released, only a bunch of players will play it. If they do not meet, their experience will be bad. They'll leave the game. Some other players will join. Their experience will also be bad. This situation happens a couple of times, and you'll end up with a game that's a complete wasteland that nobody plays anymore. This means your game is dead on arrival. But fear not, because this issue can be fixed with AI. So how can AI help your game? Well, there are actually two cases. The first one is, of course, if you are still set on to make a multiplayer only game, then the AI can definitely help you by replacing players with AI agents that simulate real player actions. This way, when an actual player joins, they have the feeling that the world is not completely empty and they have someone to play with. You can have the AI replaced as more and more people join. And this way, you won't have your game dead on arrival. If you want to make a single player experience, the AI can help you a lot. It can really improve your game. For example, let's take Fear. It's an old game, but its AI was revolutionary. Articles were written about it. It was praised as being one of the most comprehensive AIs possible. So if you want to make a special game and set it out apart from the crowd that has basic AI systems, then you should definitely look into this. Now let's look at different AI types that we can find in games. When people discuss AI, automatically they think about enemies. But that's not the only way the players experience AI systems in modern games. What are the most common types of AIs? Let's find out together. AIs as enemies. This is the most found implementation in games. Usually everything that comes to you and shoots to kill is most likely an enemy. Enemies come in different flavors to spice up the gameplay: aggressive, defensive, tactical, and much more. AI as companions. Is there a non-player character following you? Then most likely you got yourself a companion. Be it either for a specific mission or a squad-based game, companions play an important role. Games like Mass Effect or Gears of War have a lot of mechanics focused on companions. Do it right and your game will benefit a lot. Have companions going through walls, dying randomly and failing the mission, and your game's player will get a bad experience. AI as your own units. Are you issuing orders to a squad of units in real-time strategy game? Then most likely you are ordering smart AI agents a tactical decision and they handle the movement, patrolling, attacking, or any other action they have. AI can be your own character, in fact. Are you playing a top-down role-playing game where your character moves around in a dungeon? Most likely the AI is controlled by a Pathfinder that decides where to move exactly, based on your specific required move location. AI as helpers or invisible helpers. What if I told you that a game that has 0 non-player characters and in fact any other moving parts has AI? It's true. I'm referring to The Witness from Jonathan Blow, where the AI was used to debug the map to find out the walkable areas. AI can take many forms, the limit being the imagination of the developer. My hope is that by getting all this information to you that I provide in this course, you'll be on your way to make great AI systems that will improve your game. Next, let's look at how AI can handle decisions. Before we can discuss decision systems, we must first look at what makes an AI work. What are its parts? An AI agent is possible because of the following parts. The brain, which is responsible for the decision making. The senses or sensors are the AI's way of detecting enemies, obstacles, and more. They are linked with the brain to provide the accurate information in real time. The body receives the actions from the brain and executes them. And the legs are mostly used to move the character using different pathfinding algorithms. Let's now focus on the brain of the AI, the decision systems. And there are a couple of them. We will take each one and discuss it a little. Finite state machines. This AI is used a lot. Actions are mapped to states and the AI can be in a particular state at a specific time. The states are interconnected together with transitions that get triggered when a particular change happens to the agent. Specific games to this are Doom and Quake, but there are a lot of other games using finite state machines. Behavior trees are very common in most game engines, having even a direct integration in Unreal Engine. Their main selling point is that the designer can create an AI system without having to interact with any piece of code. They are very flexible to use. One example for behavior trees is of course Halo. Planning. This one is very similar to state machines. The main difference is that the states that represent the actions are not connected to each other, but rather these are connected real time through a specific algorithm that gets the best possible action sequence. This is not a common way to do AI, but it's found in games like Fear. Utility AI. The utility AI does not have a particular structure, but rather a set of rules. It's mostly used to handle complex actions like an RPG character that has multiple skills and needs to pick one or another based on the current situation. This is mostly found in RPG games or card games or games that require the AI to decide from a big list of actions. Games for this are Dragon Age Inquisition. How does the AI navigate in the game world? The agent is not only just a collection of decision-making algorithms. Those decisions need to be applied to specific contexts. For example, the AI needs to move around, avoid obstacles, get to certain targets, and things like this. To achieve this, the AI needs to be able to understand the environment, where it can move or cannot, what are the points of interest, like cover points or important locations, where is the enemy. While the player can perceive the environment by visual cues like 3D objects in forms of paths, obstacles, the AI agent needs to get a processed version of that in a language that it understands. If you use the exact environment as is, the AI will have a hard time computing everything because usually the environments are too complex. Even in 2D games, the complexity of the visual world is too much to handle for an AI instance. I'm not saying that the AI cannot handle it, most likely it can. But when we are discussing AI agents, we are always take into consideration the amount of CPU used when running 20 agents, 50 agents, or a higher number of AI agents. We need to get a simplified version of this world. Here are the most common ways to achieve this. Grids, a set of rows and columns that form a 2D table. Graphs, a collection of points that are connected between them. And Navmeshes, a simplified environment mostly auto-generated by modern game engines. Let's look at these three and see their pros and cons. Grids are the most common way to create 2D environments, but don't be fooled by their 2D capabilities, as they can also be used in 3D games that are limited to a flat surface. A grid is a set of lines, as you can see here, and columns that are put together to form a 2D table, where each point or cell can be referenced by a pair of a row index and a column index. If you want to learn how to implement grids, head over to the bonus module and look at data structures. Let's find out what are the pros and cons when using grids. The first one is that it's very easy to use. Create a 2D array of elements and it will already work with the map structure, if the map was designed to support a grid in the first place. It supports real-time changes. Does your game have actions that change the map? By having a grid, you can easily set what's walkable and what's not. And the best part is that it's already implemented in most common game engines, Godot included. All of these pros, that means that grids must have some cons, and they do have. They have a fixed shape. It will always be square shaped. Of course, you can disable the sides to make interesting shapes, but it's very much limited to that. It cannot support height variation, and if your game has hills, valleys, then a grid might not work for your game. In general, it cannot provide too much environment variation. Having a grid city might not be exactly fun in some cases. If a grid-like structure sounds too restrictive to you, then you might want to try graphs. Let's look at them right now. Do you want to have dynamic cities, maps with height variations, even breakpoints? Then graphs might be the data structure you are looking for. A graph is a data structure made out of a collection of nodes and edges. The nodes, like these, are the endpoints, and they usually store data as containers. And the edges are the connections between two distinct points. Notice here that the edges have only one way to go. This is actually a special type of graph called direct graph. Of course, they also have pros and cons. Let's find them out together. Using graphs, you can model any type of terrain, height, or whatever else you need, street intersections and much more. And it can be easily updated if the map changes real time. But of course, the graphs are much harder to work with than grids, let's say, because mostly you'll have to implement them yourself. Another option for having an environment for the AI is the Navmesh. The Navmesh, or the navigation mesh, is one of the most common ways for the AI agent to navigate on the map. Its implementation is found in most modern game engines such as Godot, Unity, and even Unreal. A Navmesh creates a simplified model of the 3D objects that are walkable using simple polygons, and then it connects them. When a path is queried, it quickly determines a way using a pathfinding algorithm called A star. What are the pros and cons of a Navmesh? It's already there. If you open Godot, you will have it. It's mostly available in every game engine. It's very easy to use, and it's also optimized for efficiency. So if you have a bigger map, chances are it will work without any troubles. But of course, it does have some cons, because it only supports a particular type of map, the one that you create with a 3D model. But if your map is, for example, hexagon shaped or has a totally different structure, then a Navmesh might not work for you. And also, since its implementation it's already embedded in the engine, it's not customizable, such as graphs, for example. Congratulations on finishing this chapter. In the next chapter, let's find about finite state machines. What are finite state machines? Well, a finite state machine, or for short FSM, is a collection of states and transitions. The states represent the actions that an AI agent can take. For example, fire, run, patrol, and so on and so forth. And the transitions are the links between these actions that tells when the AI should change its current state. For example, if the AI was patrolling and it encounters a player, then the state should change from patrol to attack, so that the AI can properly play the animation, fire the projectile, and face and run towards the enemy. This is one example, but finite state machines is one of the most common ways to implement AI in games. Behind the scenes, an FSM is basically a graph. And if you don't know what a graph is, then you should definitely check the bonus section, the data structures. What it does is basically these nodes represent the states and the transitions represent the edges between them. Let's now look at the pros and cons of using a finite state machine. Well, one of the most important pros is the fact that it's very easy to use and understand. You basically create the states, you name them, and you use them. You connect them via transitions, and basically this is it. And of course, because of its simplicity, that means that it's very fast. So if you have a lot of AI instances, for example, 100, 1000, then a finite state machine would do good because it doesn't require so much processing power. What are the cons of a finite state machine? Well, the first one, that it might get out of hand quickly. If you add more states, more transitions, you interconnect them with each other, then you might end up with a spaghetti of something that it's hard to maintain, and it's also hard to reuse because you cannot just take parts out of it because they're tightly connected with each other. But with all of these cons, I still believe it's a powerful system and it's used in modern games. There are ways to mitigate all of these risks by implementing something called hierarchical state machines. And the good news is that in the final project that we will have in this course, we actually have a hierarchical finite state machine. Basically, what it means is that it groups states together in bigger states to avoid having too many redundant transitions. But you'll find out more in the later project. Now that you know what a finite state machine is, let's find out how you can implement one yourself in Godot. Now that we have covered the basics of a finite state machine, let's look how one can be implemented using GDScript. There are many ways to implement a finite state machine. This is but only one of them. We will use two types of scripts. The main finite state machine, which is responsible for changing states and running them, but also keeping track of the values in a small database, and the others, which are the actual state implementations. Let's look first at the finite state machine. And I've already created this structure, so we will go inside the custom finite state machine and start working with it. And of course, the first thing that we need to do is create the basic structure. We will use the entry state that can be configured in the inspector of this state machine to know exactly which state should be run first. The current state is the variable which holds the current state that is actually running. The database stores key pair values when we need to access particular information about this state machine. And we also need the state list, which is also a dictionary. In the ready function, we will need to do a couple of different things. The first, we will parse all the children. So as you can see here, we have 3 states and we need to get all of them. And for this, we can parse all the children. And first, we will initialize the children's finite state machine with this one. And of course, we need to add the state list of the state name and the state. This will basically create a key pair value of the state name and the state in this finite state machine. This will be useful, for example, when we are going to change state from the entry state, because the entry state is a string, so it's not an actual state object, but this one is a state object. And by having this dictionary, we can actually convert string names to actual state objects. Now let's proceed and implement the change state function because we currently don't have it. And here we need the new state, which will be the new state where we will head into. And if the current state is not null, then that means that the current state currently has something in there. Of course, we always need to check to see if the current state is a legit state. And for this, we will use the exit state because we will call for every single state the enter state, exit state, and update state. So in this case, if the current state has an exit state, then of course we will need to call this function. And be mindful that if the current state did not have this exit state method, then this will give an error without this if. So it's important to put this check before. Next, we need to check if the state list actually registered a state with the name that we want to change with. So if the state list does not have, so to say it does not have, we can just negate the has. So instead of this, which will return true if it does have the state, then it will make it false if it does have the state. Return. This is really important because we cannot change to a state that is invalid because it doesn't exist. Now that we know for sure that the state exists, we can say current state equals state list new state. And since this is a string, it is important to make sure this check happens because otherwise this query will give an error. This is also for check, but if the current state has method enter state, then of course we need to call it. The enter state and exit state are always called when a state gets changed. This is important for runtime functions that need to run in that particular state. Now let's move on with the process. So in the process part, what we need to do is we need to check if there is a current state. And if it's not, we will call return because we don't want to process this any longer. Of course, what we could have done instead would have been if the current state is not null, and then write our code here. But the problem by doing this is that we will have more indentation as we go with this kind of structure. So instead what we do is just check if it's null and then return to keep the indentation level. So to keep this indentation as close to the left as possible. This will create a nice code structure in the long run. And here, of course, we will call current state because you know it exists and check if it has the method process. And be mindful here, this process is a little different from this one because this gets automatically called by Godot and we need a custom one because we need to call it here and we need to make sure that it only gets called here. So I'm just copy paste this because it's much easier and I'm going to put in the delta. Of course, I'll do exactly the same for the physics process. It's important to copy paste this to make sure that there's no error. Why is it important to have process and physics process? Because some functions only work in physics process. So it's important to have both of these supported in our state machine. Of course, we already have the change state. What we need to do here is create two more options, and that is set value, which is a setter for the key pair database we have. So value name and value. And DB, the database dictionary that you created, value name will be equal value. And next one we'll have get value, which can just get the value name. And here we can say if the database has value name first, because we cannot query something that doesn't exist, then it will return the database value name. This is important because our state machine will need to communicate with different states to know what is the current state of the whole system. For example, is the player retreating? Is the player attacking? So on and so forth. So we need to have a synchronized database for all of these states. Now let's move to a particular node implementation, and for this I will target the idle state. So first we will need to have a reference to the custom state machine that we just implemented. And now we need to make sure we have enter state. And as you remember, the enter state is called when a state gets changed. So this will be called when the idle state is changed. Now we also need the exit state. Make sure that the names are exactly the ones used in the custom finite state machine, otherwise it won't work. And here the process, it's not with underscore because this will be automatically called every single frame from Godot. And it's important because if you have multiple states, we don't want them to run without any control, but instead being able to control them through this process. So in order to make this happen, we need to make sure that it's not with underscore. And this is basically, you can call it whatever you like, but I just called it process delta. And here, before we actually do any process from the state, we need to check the conditions. And the conditions are really important because they will tell us if we need to go from this state to another one based on some values that are stored in the database. We will create these and the other states in the mini example for the finite state machine. Let's find out how to make them. In this example, we will have three different states: the idle state, the move state, and the fire state. These are basically just some scripts with a little code. They're nothing special, but of course you can imagine that this is an AI because it can be an actual AI here. Every state will be connected with each other and will trigger transitions when specific conditions are met. Let's configure the finite state machine example first. This will be the main screen, which currently has two buttons, is moving button and is firing button. Basically what they'll do is have a special signal that is called in this debug script. And this debug script, what it does, it has two signals from is moving button and is firing button. And it will set up two states and will set up inside the custom finite state machine that we created the database with the is moving or is firing, and you'll also reflect this in the button text itself. Also, we need to show the current state in a label. So if we go back, the current state will be visible in this label to be able to properly debug it. Now let's go back a little to the idle state, because we need to make some changes here, because we will have some connections between idle state and move state and fire state. So if the finite state machine, by the way, in this implementation, in the check conditions, we will create the transitions for various states. So we need to get the value and is moving. And be mindful that this value is actually set in this debug script, so is moving, it needs to be the same. I can just copy paste it to make sure it's the same. Otherwise, what I recommend you to do is create a globals file. You can do that by using a singleton in Godot, and basically create a variable that has this string and use that variable instead to remove the hard coding part, because by just missing one character here, then it won't work anymore. This is a pro tip basically. So get value is moving, and of course this is true. Then we need to change the state to the move state. How is the move state called? Well, it's actually the same name as here. And if you remember from the implementation, we get every state from the children. We create the dictionary with key pair values. So based on the name actually written here, we actually get the state as well. So this is how we go to the move state. And now, of course, we don't want to continue this because we already changed the finite state machine to the move state. But if it was not moving, then it might be a possibility for it to be shooting or is firing. And if that's the case, then we need to change it fire state. And by changing to the fire state, then of course this is a new state. And in the move state as well as in the fire state, we see very similar code, but we just check for the values in the other direction. Just be mindful that some changes here are really important. So as you can see in the move state, it's a little different. The if statements are embedded as well as in the fire state. This is important to prevent unusual transitions in the state machine. Before we can run this, I need to set up the entry state in the custom finite state machine. And of course, I want it to be idle state. So with this entry state running, by the way, if we run the state machine without this, it will crash. So make sure to actually put this here. If we run this, then of course the current state is idle state and we entered the idle state. If the enemy is moving, then the variable is moving will be set up. In this case, I'm just going to set it up by pressing the button. But as you can see, we exited the idle state and we entered the move state. And the current state is of course the move state. If I put in the firing, as you can see here, the move state is still going because of the way conditions are created. So it will go to firing only if I disable moving. And basically what it does here, it goes back to idle and then checks, oh, is firing is online? And as you can see here in the moving, so exited move state, entered idle state, exited idle state, and entered fire state. And this is how we end up in the fire state. Be careful how you create your transitions, because this will affect your whole logic of the finite state machine. Basically, this is all about finite state machines. Now let's find out in the next module how to get an AI from a position A to a position B using pathfinding. Here we are at pathfinding. Pathfinding basically means an algorithm that, given the point A and point B, of course they should be different, it returns a sequence of steps that any object from point A can take to arrive to point B. Usually these steps are optimized. That means that it tries to take the shortest route possible. At the core, Pathfinder searches a graph from a starting point to the end point from neighbor to neighbor. An algorithm that's mostly used in game development for pathfinding, it's called A star. This is mostly hidden between layers upon layers. For example, even in Godot, you can call it via a function and you don't know what exactly happens under the hood. This is good and bad at the same time. The good part is that everything is kept simple. You just use it, set it, and forget it. The bad part is that everything is hidden from you. And if you want to customize it, you tweak it a little to make your game special, then you will encounter some issues because, well, it's basically a black box. But don't worry, because in this module, we will be creating our own Pathfinder from scratch. It's not as efficient as A star, but it's quite efficient for a lot of game types and also for some structures that cannot be achieved with A star, such as a flow field. At the core of every Pathfinder, there are two parts, the domain and the actual algorithm. Let's find out about each. The domain, or also the space, is where the algorithm happens, where the AI knows what is a wall, what is a space that it can move, what are some other obstacles, and some destination targets. And it's important for the domain to have these characteristics. Fast. The domain query needs to be fast because when you have 100 units doing the same queries over and over again, then if you have a complex 3D environment, then not being fast means that your game will be lagging and it will give a bad experience for the player. For this, we need a simplified version of the environment. One example of this is called Navmesh or navigation mesh. The domain also needs to be reliable. That means that any domain that provides wrong paths through the walls or through obstacles is bad because, of course, it's clearly not working as intended. So every query to the domain should be similar to what would be in the real world example. And lastly, the domain should be stored properly. And what I mean by this is using the correct data structures, because if you use the wrong data structures, then it will take time to query the actual domain. So of course it needs to be stored in the proper ones. We will use graphs for this. Now let's look at the algorithm of a Pathfinder. And there are many algorithms to do it. A star, Dijkstra, depth first search, breadth first search, and much more. What they have in common is that they give you from point A to point B a path. They work differently, and most importantly, they have different speeds of execution. So some are faster and some are slower. But of course, they do have slightly different results that can be used a little in more or less ways. The algorithms can be categorized in two parts, uninformed and informed. Uninformed means that the algorithm doesn't know more about the environment except that what's a wall or what's a space that it can use. Informed means that the algorithm knows a lot more. For example, this terrain is a swamp, this terrain is grass, this terrain is ice. So of course it has much more information about it. In the next chapter, let's look at the pathfinding algorithm. The anatomy of a pathfinder. How does the AI know how to get from point A to point B on a map? What is the code sequence that enables that? The code is an algorithm, and there are many pathfinding algorithms out there. In this chapter, we will look at a simple pathfinding algorithm called breadth first search. BFS is an uninformed algorithm that deals with the situation at hand. Its end result is a path between the starting node A and the final node B. Let's deconstruct the algorithm and see how a pathfinder works. We will start by defining the space. And for the space or domain, we will use a grid because it's one of the most easiest ways to implement it. Any position on the grid can be referenced using two indices, row index and column index. For example, these positions. Regarding the implementation, a grid can be simply implemented with a list of lists or an array 2D like this. So it has one list that has multiple lists and each value represents a cell here. Of course, it's good to know that we need to fill the space in order to simplify our edge cases. And for this, we'll consider the wall being -1 and the empty space being 0. And we will mark the exterior of our grid with -1, which is the wall. Let's quickly go to the queue. By the way, if you want to know more about the queue, there is the bonus section where we discuss about the queue in much more detail. But basically the queue is just a list with a spin. You can only add elements at the end of it, and you can only remove them at the beginning of it. This is very similar to a cinema queue. The queue is an important part of the breadth first search algorithm. The next step is, of course, to study how we are going to move through the grid. And if we take a position, let's say 3 and 3, line 3, column 3, or simply 3, 3, then we can adjust the up, down, left or right movement by adding or removing one step to either the column or the row, because you only move 4 directions, and these new pairs of values will be the next positions for our object that has the pathfinding algorithm. How can we encode the movement patterns to be easily processed by the algorithm? And for this we will use two lists called dx and dy. Of course, you can name them as you like. Basically, they'll encode each step. So for example, if we take the pair that was 3, 3 initially, and if I want up, I need to add -1, which will be 2. And for the y, I need to add 0 because we only move row and we don't move column. So of course, it's 0. Let's take for the right, which is 0. So we don't move a row. So the row needs to stay on the same one, but the column increases to this one. For the down and left, it's the same. Here's the example. As you are taking the 3, 3 example, by adding each of these pairs, we get these new values that are representing the adjacent positions. Of course, by just adding more pairs to this list, for example, 1 and 1, you'll get this value, this value, this value, or this value. By doing this, you'll enable your AI controlled Pathfinder to work with 8 directions instead of 4. Of course, you can even put more exotic directions, for example, like a knight in chess, to move in L shape. So for example, encode this position, it needs to be L shapes. But of course, you can have any type of direction you want with this structure. Now let's look at the algorithm itself. Luckily for us, it just has only 8 steps. First, we need to add the starting point to the queue. While the queue is not empty, we need to get the first position, and if the first position is the destination, then the algorithm reached its goal and we succeeded. Yay! But if it didn't reach the position, then we need to get the adjacent positions. This can be done with the lists dx, dy. Then we need to fill the positions and add them to the queue so they can be processed in the next step. Of course, I also prepared a code because it might be much simple to see it in actual GDScript. The queue, as you can see here, is just a list. I'm using Godot Next, which has an array 2D, so it has a grid-like structure, but basically we are adding the first position here. While the queue is not empty and the exit was not found, we get the current position. Basically, this is kind of the same, but this gets the value of the current position because we will also put in the steps. So for example, the first step is 1, and then the next step is 2, 3, 4, until it reaches the end position. We only have 4 directions, as you remember, dx and dy, where we get the x from the current position, we add the dx at the I position, and the same for the y. Of course, we get the next cell step. If the next cell is final, which is of course if it's the goal, then we don't need to work with it. But if the cell is empty, and this is really important because it can be a wall, and if it's wall, we don't care about it. If it's empty, and then we can add this new position to the queue, and also here I'm just adding the current step plus 1. So for example, if the first step was 1 and this cell is the next one, then it would be 2. As you can see here, if you start in this position, the first step is 0, but then the next step, the adjacents are 1, then the next positions are 2 for these steps. Basically, they mean how many steps you need in order to get there from this initial one. And so on and so forth. By applying this, we end up with 7 steps to position B. I want to make an observation here. Running BFS like this, it won't give us a path from A to B. It will just fill the map with how many steps you need from A to reach a particular position. To get the actual final path, we need to do something called reconstructing the path. And we do this by getting to the last step of the algorithm, which is the arriving at the position B, and then we will use a recursive function. Basically, a recursive function is a function that has a call to itself inside of its code. You can find more in the bonus section for this. We'll be using this code to remake the path. Let's quickly go through it and try to understand it. So the first thing is we will use the current positions X and Y, which are the end position. These are the total steps that we reached so far. We get the current position and the current cell. This is very, very important because we will be using the previous cell step in order to advance backwards through our algorithm. So in this case, let's say we are here at 5 and we want to know what is the lower step basically. So we won't go back to 6. We only can go to 4. So these are the only possibilities. If you are at 4, we cannot go back to the 5s. We can only go back to the 3. If the current cell is start, then that means that we have arrived at the destination. Here it is setting up the color, but basically this is it. And if not, then of course it does the same. It takes the same direction lists. So of course we need 4 of them, and we get the next position and it needs to check if the next cell's value is exactly 1 less than the current one. Or in this case, if we add 1, it should be exactly the same as the current step. And of course, if the next cell is not a wall. Of course, the final color is not important for us. This is for the algorithm to look nice, but it just returns remake path, and as you notice is the same name as this function. This means it is a recursive function. And basically this calls this function again, but from the positions of the adjacent cell. So if we go to the final result and are starting here, basically calling this function here, we'll find this position and we'll call this function from this point. When this point is achieved, then it will call from this one and from this one. And the end case is when it's called from this one, and from this point, the next one is actually the original cell. And this is how this function is called. And it's really important when doing recursive functions to have this exit condition. Otherwise, the function will call itself indefinitely and it will crash your game. So make sure you have this in mind when implementing recursive functions. And by running this function, you will end up with the final path. And the final path can be used for the object in the position A to move to position B. What are the pros and cons of using BFS? The pros are that it's very easy and fast to implement. It's very easy to debug and also very easy to visualize, and can be used in various scenarios. And its major con is that it's slower than A star. It's actually useful in some cases, for example, generating flow fields in real-time strategy games. But it's not quite useful for large data sets, as it will take much more time to process them. BFS can be used for quick custom implementations. Alternatively, you can use the already created A star implementation in Godot. They work similar, but A star is more efficient. In the next chapter, we will look at Godot's navigation mesh implementation and how to use it. Now that we have implemented our first pathfinding algorithm, breadth first search, let's put it to the test and execute it with a grid. And you can find this example in the attached project for this course, but I'm going to quickly show you how to use it. So you have the left click to put a start position, left click again to put the end position, and with the right click we can specify some walls between our two positions. This will actually make the map harder for the algorithm. And if we click execute, then we can get a step-by-step path from the origin to the final position. Now let's see if we put a start position and an end position and execute the algorithm step by step. So the first step is actually to check the direction above. So we'll see the next position is labeled 2 because we need 2 steps to go here. And in our queue, we have 1 and 2, which is this one. It's line 1 and 2. Please know that the first line is 0 and the first column is also 0. If we click next step again, then the right position was checked, but it's a wall, so nothing to do here. The next one will be down, so another wall, nothing to do here. But the left position in this case, it's okay, so this will be added to the queue, as well as the step number would be updated with 2. Now, if you proceed, the first one to get out of the queue would be 1, 2, which is this one. And we'll check top, left, down, which is already parsed, so we uncount that, and left. Let's do it. As you see, this position ended because there's no way to continue. So the algorithm will just continue with this and this. And boom, now we have the end position. So this is how breadth first search works. Of course, it is good to keep in mind that this is the first step because we need to recreate the path. And to recreate the path, we use the recursive function that we discussed in the previous section. Let's now look how to implement the navigation mesh in Godot. If you use 3D objects to define your terrain, you are in luck. Godot provides a solution for you out of the box. Enter Navmesh. It's quite easy to create and use a Navmesh because Godot provides 2 key nodes for it, and these are the navigation node and the navigation mesh instance. By putting this node and the child node navigation mesh instance, we can generate a navigation mesh by running the bake navmesh. Of course, for this, we definitely need more of this, so I'll quickly create a small environment that we can run our navigation mesh. Now that we have these in place, we need to select the navigation mesh instance, and as you can see, there is a small error here because it needs an actual nav mesh specified here. But don't worry, by just creating a new nav mesh and hitting the bake nav mesh, Godot will automatically generate this awesome nav mesh for us to use. Of course, to actually get a position from a point to another point, we need to use a particular instruction, and let's find out how to implement that as well. So first, I'll need to create another mesh instance, which will be our player, and our player will be just a capsule. Make it a little smaller. And I'll give it a script. So what we need to do here is, of course, get a reference to this navigation, and this can be done at the start of the sequence. So navigation, we'll call it, get parent, because the parent of this is the navigation. And then we will use a get custom path target position. We will want a path from that target position. So we can generate it by calling nav get simple path, and then we need to specify the start and the end of the path. The end is the target position and the start is where the player is. And basically this is it. Of course, to be able to test it, we need to go back into the scene, and let's create another position 3D, which would be the target in our case, and let's put it around here. I'm going to call it in ready, so I'm just going to print out get custom path from the, of course I need to go back one level because the player is up on level. Target. And then we need to get the position. And by doing this and calling this, we will end up with a list of positions, a vector tree that the player needs to take in order to go from the initial point to the target that we specified. Welcome to sensors. In order for an AI to take actions, it needs to do two things. First, to understand its environment. We discussed this in the previous chapters. And also to sense its surroundings. That means enemies, useful items, useful locations, and much more. These senses can be taken from real life and then implemented. For example, sight, hearing, touching, for example, if the AI gets hit by a player's bullet. In this module, we will be discussing about sight and hit. And in the sight sensors, we actually have three different categories. We have the range, which takes all the stuff around it. The view cone, which is basically what's in front of the eyes of the enemy. And also a raycast, which checks if the object that should be visible, it's not occluded by a box, for example, or some obstacle that is between the AI agent and that object. Let's look now at each of these sensors and see how they are implemented. Welcome to the sensor implementation. And the first sensor we are gonna look into is the range sensor. First, let's give this scene a quick test run so you can see what we are going to achieve in this module. We have the enemy in the middle of the scene that has a range specified by this wire sphere. If my player, which I can move with WSD or the arrow keys, goes into this sphere, then it is detected, as you can see here, and if it's out, then it's false. This is a quite simple sensor. It's not useful in cases where, for example, when you want field of view, but in some other cases, for example, turrets or things that have 360 view, it works great. Plus, it can work with other sensors together. So let's see how this is made. Okay, now here we have the scene. And as you can see, there are a couple of different components here that I want to discuss before diving deep. So we have the AI in the middle, which is basically the AI instance that has the sensor. We have the terrain, which is basically just a cube. We have the target, the camera that we can see through while the scene is playing, and the control, which is basically just some UI elements. Let's quickly look at the target because this is the player. So here there is a kinematic body. It's important to be on layer 1 because the detection will be on layer 1. It has a mesh instance, which is a capsule, and a collision shape. Don't forget, it's really important to have the collision shape. In my case, it's a capsule shape, but any shape works. For the target script, if we look into it right now, because it's quite easy, it just sets up the type of the enemy using the meta functionality. And the collision, this is not relevant, but it's used to detect the body which has the collision. If we go back to the scene, we also have the range sensor test that has a script attached to it. And this is really important because this is the debug script. What this debug script does is, of course, initializes the range detector. By the way, here is the radius. So if you increase this, then the sphere will get bigger, the detection sphere. First part says if it's enabled or not. And lastly, it gives the AI. In this particular example, this is not so useful, but in the real world example, we want to avoid detecting itself. So we don't want the AI to be able to detect itself. So this will actually work to remove the AI from being detected. In the process function, which happens every single frame, we do have move up and down and left and right, which move the target up, down, left, and right. Also, the range detector provides a target list, which we query all the time, every frame, to see if its size increased from 0. And if it does, then this statement will return true and will appear on our UI that is detected as true. Otherwise, it will be false. Now, let's take a look at the AI and what does it have. Basically, the AI is just a node with a mesh instance, which is a capsule, as you can see. But the important part here is the range detector. Currently, there is no physical part that can interact with the range detector from the AI, but in a real case scenario, there will be. Let's look at the range detector. By the way, I created a special scene for this to make it reusable as possible. So if I click open in editor, it will open the new scene. And here there are a couple of things really important. First, we have the area collision. And it's really important to create this area collision because this will determine the collision between this object and what comes into it. Please make sure that monitoring is set to on. Monitorable means that it can be queried by other things, but since we are the ones that are monitoring, we can safely put this to off. We need to put the mask on 1 because the layer of the player is on 1, so we need to make sure this is on 1. The collision shape for this is a sphere, so this is put as a sphere, but this will not matter because you'll change it through code because you want it to be dynamic. There's also an immediate geometry. This is for debug purposes, but what I can tell you about this is just a simple immediate geometry node. It has a material of yellow without lights, so it's unshaded. And also here, it's quite simple code, but basically what it does, it just creates a sphere out of primitive lines using the radius provided by the collision sphere in the range detector. It's nothing fancy, it's just for visual debugging reference. Now moving on to the main part of this is the range detector script. And here's the full script. We're gonna look into each part and see how it works. Basically, starting from the top, we have the extends node. It can also extend the spatial since it's a spatial, this one. It provides two different signals, which in some cases you might use, in some cases you might not. But on the target enters this range detector, it will signal that fact and also send what target actually entered or what target exited. Next, it will have a target list continuously updated with all the targets that are monitored in that range. The collision shape is the sphere shape mentioned here, and this will be used to make the correct size when we actually customize it. The parent is the actual component that we want to take out from the potential target list. For example, if the AI detects itself, we don't want it to be in that list because it would be redundant. Is enabled, of course, is self-explanatory. True if it is enabled, false if it's not. Here we have a couple of different functions. Two of them are custom and two are signals from the area collision. Starting with the initialize, it says is enabled, custom range. This is what actually gives the range of the whole sphere. And the parent. The collision shape, as I mentioned before, why this is not important, this sphere shape, because we are going to create a new sphere shape and we are going to set the radius of the sphere shape to the custom range that we provided. Next, of course, we need to initialize is enabled and parent from these two values. And for the collision shape, we need to, of course, set it correctly with the one that we currently created. And if is enabled, of course, the immediate geometry gets the collision sphere as well. The main part of this is the function called isTargetInRange, which will give true or false. But as you can see, there's no query to physics, but more a query to if the target is in the target list. And this is because the target list will automatically get updated with things that come in or out of it. And this happens because of the next two things. So how we can hook up the signals? Well, if we go to the area, and we go to the node and on body entered. So it's body, not area, because this one is the area. The player kinematic body is a body actually. And here just say connect. Of course, we need to put the range detector because this is the script where it has the connection to. And when you go back, we repeat the process for both of them. When you go back, we end up with these two functions. And as you can see here, they are connected. What happens here is that the area detects a target that entered. And then the target gets processed into an enemy. Here I have a singleton called globals, which has get enemy from collider. We'll quickly go into that in a second. But before that, if the enemy is not null, that means that it was processed correctly. And the target list does not contain the enemy. This means basically that the enemy is legit and it can be added to the target list since it's a new enemy detected. First, of course, we need to prevent the self-collision, what I said with the parent. We don't want the enemy to be itself. And then we use append for the target list, which is basically a way to add new elements to the list. And then we emit the signal. We send the event that, hey, this target entered the range. In the case, for some reason, this happens and the enemy detected was already in the range, then it won't be counted as a new enemy getting inside this list. The same happens for a target exits. So basically it still determines if the enemy is valid, and then if enemy was actually in the target list, and if it was, then it needs to be erased, and then another event is released saying that the target is out of range. Now let's quickly look at get enemy from collider. So here is basically a physics collider. So in this case, what we're gonna receive is probably this kinematic body. So keep this in mind. And the kinematic body, as you remember, we have this small script that has a meta tag called type with the value enemy. And this is really important in what's to come. Because if we go here with control click, basically it gets the enemy from the collider. It's just a value. And then it checks if it has the tag. And that means that it is detected. And if it's not detected, then it will return null because there is no enemy to detect. But then, of course, we need to process the tag and to see if it's actually an enemy or a player. And both of them are labeled as enemy. This actually happens because in the plan is for the enemy to target both the player, but also enemy AI from different teams. So this has to happen in order to do this. If the tag is not enemy and not player, it might be a third party type, like for example, obstacle or something else. And we don't really need to count it as a target. So for this, we return null because we don't need it. Now, if you go back to the range scene and test it again, this is the result of this. And if we quickly check the target list, so I'm going to take the target list, I'm going to print the target list. And as you can see, the target list is the kinematic body, but if I step away from the range, the target list will be empty. Go in, the kinematic body, out, empty, in, out, in, out. Very simple. This is basically the range sensor. Now let's move over to the field of view sensor. Welcome to the field of view example. If in the first sensor implementation was the range where it detected around the enemy, the field of view is actually helpful when we want to detect in front of the enemy, specifically by a given angle. Let's give this scene a test and see how it looks. So if I press F6, then we end up with this, and the field of view is 60 degrees, so something like this. So of course right now I am in the field of view, but if I move out of the field of view, then it's false. So basically this is what we want to achieve in this sensor. By the way, please keep in mind that if we use just the field of view, this will actually propagate infinitely. So basically, if we enlarge these segments to infinity and have the player here, it will be true for every distance. The solution for this is actually to combine both range, because range will give the list of the objects around in a specific distance, and then the field of view, which will limit it from the front view. Please note that this is really important if you want to use this field of view implementation. But now let's look at the code. First, we have the AI, which has the field of view detector this time, and the terrain, the target, the camera, and the control are similar to the previous range scene. Let's quickly give this a look because it might be interesting. The main change here is actually the fact that the field of view detector does not use a list, but basically is a query. Is the target inside of field of view? Yes or not. So if it is, then it returns true, not false. The target being the target given here. So let's see now, what does the field of view detector look like? So I'm going to open this. By the way, it's a new scene. So in the field of view detector, there is just the field of view. So I'm going to head into the script, and here The code is quite simple, but there is a little math, especially vector math involved, but don't worry, we'll quickly check it and look into it to see how it's done. So of course we need to specify the field of view angle. This is really important and it's 60 degrees. By the way, please note that Godot uses radians, not degrees, so you need to be careful to convert them to radians when using them. So let's quickly discuss what we have here. First is the enemy position, which is the red circle here. We have the direction, which is the forward of the enemy, which is here. Please note that this direction is normalized, it's 1, of length 1. And the target position, which is the target position point, which is this green one. And if we run isInside cone, then we need to compute the difference vector, which is the difference between the target point and the enemy position, which is this vector, but it needs to be normalized, and normalizing this will mean that we need to put this length to 1. So in this case, it will be this small one. Please note that the direction is the same, though the origin is the same. I just put it parallel so you can see the small one. Basically, this is the same, it's just normalized. And then we need to compute the dot product of these two vectors and then compare it to this cosinus. What this means is that if we do the dot product between the two vectors, and stating by the Godot documentation, so it basically, if the angle between them is straight, so that means 90 degrees, then it will be 0. If it is greater than 0, then the angle is narrower than 90 degrees, and if it's more than 0, then the angles will be wider than 90 degrees. But what this means for us is that it will give a value between 0 and 1, and then we can compare it. Of course, not directly, we need to compare it to the cosinus of the actual field of view, but it needs to be divided. And of course, as I mentioned, this is specified in degrees and we need to have it in radians, so we need to convert it. And then we apply cosinus on this. If it's done right, so let me quickly print this out because it will be much more clear how this works. So putting the difference vector. So here, as you can see, it's almost 1 when they're perpendicular. That means the angle between them is basically the same. But if the angle gets changed, then this value is actually the cosinus between these two angles. So as I can move, and if I go on the other side is the back, the values will be with minus, but that is not important for us. The important part is the plus values. And I'm going to quickly also put the cosinus for reference. So the cosinus for this is 0.86. So basically, by using this field of view detector, we can detect if the enemy has direct vision of a target in a specific line of sight. What happens though if there is an obstacle between the enemy and the player? Well, in this case, we need to use Raycasts. Let's find out how to implement that in the next session. Welcome to the Raycast part. In this session, we are gonna look how the Raycast sensor is implemented. If you remember, we went through the range sensor, which casted the range around the AI. Then we looked at the field of view, which looked in front of the AI. But this case is when the field of view fails, because if the player is in front of the AI agent, but it's occluded by a cube, then the enemy will still be able to detect it. To prevent the enemies hitting you through the walls, we need to use raycasts. And raycasts are actually lines that are more physically based. They are not visible. In this case, I'm just using a debug line for illustration purposes, but rays are invisible lines that are casted from a point towards a direction. And then whatever they intersect in their path, it returns that. So in this case, it will be this cube first. So the detected is false. But then if we move, the detected becomes true. And then of course, I'm trying here with different obstacles. And this is the result that I'm getting. So basically, this is what a raycast does. Let's see now how this is implemented and how can you use it in your own game. The main structure is very similar to the other range scene and field of view scene, with the main difference, of course, being that this time we have the raycast detector. So this is probably where we need to go check, but I also want to mention that I put some obstacles, and the obstacles here, they do have a static body with a collision shape. I opted to put them on layer 10, so we need to make sure that the raycast works for layer 1 as well as layer 10, otherwise we won't detect these collisions. But let's move on into the raycast detector. So I created another scene for this because it's much easier to have it modularly. And let's look now, what does it have? So I'm using a debug hit, which is actually just a simple sphere. This is used to show the exact point where the ray hits the object. The raycast, which is actually a node that you can make by create a new node and then raycast. This will give you this object. This object, you can actually specify what layers do you collide with, and you can give it a position by moving the object around, and you also can give a direction here. So it actually points down, but this will be changed at runtime because we actually need to point this towards the player and then make sure that it actually hits the player. This doesn't come enabled by default, so make sure that you have it enabled, otherwise it won't work at all. And the debug line is just a line that makes it visible for us to see. There's another way to debug physics objects. So we go to debug and put visible collision shapes to true. And if we run this scene, then you'll see that this capsule shape, this ray, is actually intersecting the line I'm making, and also these shapes and any other physics shape is basically visible. I'm going to turn this off because I already have the debug line for this. But what's the most interesting part is this script that is attached to the raycast detector. And let's see what's inside. And here, of course, we have a couple of things. I opted to use is enabled and initialize. These are not necessary. I'm using this because they will be used in a sensor manager later on. But the most important part is what's inside is target visible. And in here, you see it's just only one function, but it does a couple of different things. First, it gets the target, which in this case it's the player, either detected by the range sensor or the field of view sensor. Then I'm getting the origin point, but I'll be getting that from the collision shape. And the collision shape is basically the collision shape of the object instead of the actual mesh of the object. And I opted to do this because the mesh rotates a little differently from the collision object. So I want to make sure that the ray is always pointed towards the center of the collision. With the position, we cannot put the cast to value just yet because we need to get out of this position the direction. And basically the direction is a vector of length 1 that points from the enemy towards the target. So how can we do this? Of course, we need to take the target position, and then we can actually get the ray position, which is the exact position as the AI agent. And if we do a vector subtraction, we actually get the vector, but the thing is the vector is of length in between them. So to actually set it to length 1, we need to normalize it. And this is how we have the direction. Of course, you need to assign this direction to the cast to value for the raycast. Make sure to multiply this a little more so the direction is actually further, because I've noticed that if it's exactly as the player, then it might not detect the collision good. So try to multiply this with a number, not so big, not so small, but this will actually increase the chances of the collision being detected properly. And then I'm using this force raycast update. This is actually necessary to update the collision information. This is required instead of waiting for the next physics process call. So make sure to update the raycast before. And then this is just for debug purposes, so I won't go into much detail, but the line gets the 2 points needed to create the ray, which is the origin point of the ray and the final point. And the most important part for us is this if statement, which checks if the raycast is colliding. And if the raycast is colliding, then we need to get what collider is here. So if the collider is equal to the target, that means if it's the player, then it will return true. If it's not, then it will return false. So basically, if we give the player as the target for this one, and the ray doesn't have any obstacles between the AI agent and the player, this will return true. If it finds an obstacle on the way, like in this case, the cube, then it will return false. And this is how a raycast detector can be implemented. Please make sure to set up the raycast position correctly. So in this case, it can go from the enemy's eyes, but if you don't assign it correctly, it might go from its legs. So make sure that it's from a point where the enemy does have its eyes or the detection functionality. This is it. And next you'll see how the hit detection gets implemented. So basically, if this AI agent gets hit by another opponent, be it the player or another AI. Let's find out how that is implemented. Welcome to hit detection. Basically, hit detection means that the enemy, when it gets hit by a projectile, it needs to be notified, hey, wait a second, I have been hit. Let's find out how this works. So if I run the scene and we think this is a projectile and this is the enemy, if we move the projectile through the enemy, then a hit was detected in the output. Of course, multiple projectiles will yield multiple hit detected results. This is important because if the enemy does not directly detect the player, but the player hits the enemy, then the enemy should retaliate. Let's see how this is done. First, as you can see, there is no player actually, it's just the bullet. And the bullet has a mesh instance, which is not so relevant just for visual purposes, but it has an area. And this is important because this is how the collision will happen. It has monitoring turned on. And there is a collision shape, which is a capsule shape. Please note that the collision shape is a little bigger than the projectile. This is just for the demo purposes to make it easier to use. Now let's see about the bullet. By the way, please note that the area has on area entered, and this signal is getting triggered in the bullet. So basically the bullet script is quite simple. It just detects if a body entered the area, it gets the parent of that object, and then if the object has the method called register hit, in this case, for example, the AI will have implemented this method, then it calls it. If not, nothing happens. Now let's look at the AI. So here the actual collision happens in the kinematic body. By just having the body in the bullet, we will not get the register hit, which is a level above it. So of course this get parent needs to be used. By the way, pro tip, make sure you have the same structure for the enemies as for the players, because if you have a generic projectile, then in some cases this might be at the body level, in some other cases it might be at the parent level, and then you have to implement either checks for just the body if it has this register hit, or the parent and the body, and it will get messy. So make sure you have the same structure for every object that needs to receive a projectile. But in this case is the higher level. So here is just a register hit, and of course it will print hit detected. Then this can be later included in the AI's decision system and tell, hey, please attack the player now or retreat or whatever. So basically, this is the hit detection. Now that we have covered how to deal with sensors, state machines, let's head over to the last part of the course, which is the actual project. I'll see you in there. Welcome to the project section. In this video, you will learn how to get the most out of the project. The project is an important part of the course. You will find here not only the examples, but a full game AI project that you can study and use in your game. Let's take a look at the file structure. From the folders 01 to 06, there are examples from the first modules in the course. They contain scripts, scenes, which you can run to find out about various functionalities. But the most important part is of course the demo one. And in here, you will find the full Game AI project as following. The main scene is located in Scenes, Demo Scene. Please note that this project is already configured to run this scene as the default one. The different functionalities are then broken down in various folders. And one decision I took when making this was to keep the scripts close to the objects that use them. This is why in the scripts folder, you will find only generic scripts. For the player and the enemy scripts, you'll need to head over to the prefabs folder. And here, let's say enemy, and you'll find the generic enemy script, and for each enemy system, the scripts will be here. They are nicely organized to serve their individual purposes. The project is also highly modular. This means that most of the functionalities are individual objects that get attached to the enemy or the player, and one such object is the HP system. And you can just take this out from the project and use it in your own, but this is highly modular and can be easily used in the AI, in the player, and any object that needs to take damage and actually die at some point. There are also other folders here for particles, shaders, materials, and much more for you to explore. Good luck on your Game AI journey. Welcome to the main player functionality. In this video, we will dive deep into the player and how its main functionalities actually work. Here in the main scene, there is the player instance, but the player is actually a scene in itself. So we're gonna head right into it. What are the main functionalities of the player? And this is important. So if I quickly play this, you'll see that the player can rotate the turret. It can move with WASD and also the arrow keys. And also it can fire, so the turret will move to a specific position where the cursor is pointed at. And if you press the left mouse button, the tank will fire. So basically these are the main functionalities of the player. There are a couple of hidden ones, for example, the turret animation. So as you can see, the turret slightly moves back, and also the tank body slightly moves back. And if I aim in the other direction, you see that it moves in the other direction. So this is also in place. This is basically a game polish thing. It's not a functionality, but we will also cover this in this episode. Okay, so let's deep dive. So the player, as I mentioned, is a self-contained scene. Inside of it, there are two main parts, the dynamic one or the moving one and the static one. And basically the moving one is the actual player mesh and the collision and things that the player actually moves when they press the keys. The systems part or the static one is the part that actually stays in place all the time. So I took this decision because in some cases, some systems and some functionalities do require a fixed position in the scene. And instead of taking it out from the player, it's better to have it self-contained because they're in fact functionalities of the player. But we'll get into that a little later. As I mentioned, the player body is the moving part. What does it contain? So of course it has the player camera. And the camera is what actually makes the player visible. But in this scene, we have two cameras that you can cycle through. So if I play it again and press C, we have this big camera, which is actually a scene camera. And this is the player camera. So this is you experience as the player camera. So this camera moves with the player. The movement is done automatically because the camera is a child to the player. So that's easily fixed. Next, we have the 3D mesh of the player. So this is basically the 3D models that make the player up. We also have the collision shape, which is a box shape in this case. This handles the projectile collisions with the player, but also the collisions with the buildings, so we don't let the player go through the buildings. It also has an animation, which is the turret animation. We'll get into that a little later. And also an HP system. This will be discussed separately, but I aimed to have the systems as modular as possible so that you can use them in your own project. So basically this is just a drag and drop, and basically you can do the same in your own project. The HP system is basically the only system right now that is in the player body. The other systems are in systems. And this is mainly due to the fact that when a projectile enters the collision with the kinematic body, it's easier to just get one of its nodes and check if it has the HP system. Otherwise, I would have to parse all this player tree and get the HP system from the other part. And that would have been a little messy. Note that this structure will be followed exactly for the enemy as well, so that the projectile code doesn't need to change if it's the player that's hitting or the enemy that's hitting. The static part consists of the three remaining systems, which are the player mover, handling the movement of the player, the targeting system, when the player moves the mouse around, the intersection between the plane and the mouse will be where the target is positioned, and the weapon system that handles the firing of the actual weapons. Now that you have a basic idea of how the player is structured, let's go from top to bottom and deep dive into each one of these and check them out. At the topmost level, we have the player script, which is responsible for gluing everything together. So what we have in here is, of course, some parameters, and then one really important one is this meta tag, which is type and player. This will be used for projectile collisions. There are two functions that handle the changing of the color of the player tank material. So init color, which gets the current material from the mesh. I made it so that most of the materials are on the position 0. Then it duplicates. So one issue in Godot is the fact that the materials are shared between instances. So it's really important that it gets duplicated. And then there's the second function called change material. This will actually go through the tank mesh and apply the highlight material, which is our new duplicated material, to all the components. Once this is done, the highlight material will get its color changed based on the team color specified in globals. So basically this is just a tint of green. The change material, on the other hand, is a recursive function. That means it calls itself. And while calling itself, of course, it may call to infinity. But in this case, since the nodes of the tank mesh are limited, it won't call itself to infinity. So we are lucky with that. So what it does, it takes the current tank mesh, so in this case, this one, and then it parses through its children. So the tank turret normal, tank body. And if the children is a mesh instance, then it will change the surface material to the material we specified, which is our new duplicated material. Note that there's one small hack here, and this is because one of my modeling mistakes, I assigned the material that we want to change on index 1 instead of 0. So this is not relevant if you do it correctly. So just take this out and just use the first one. So basically this is what it does. And of course, the change material calls itself, but it calls itself for the node. So for example, we call it first here, and then it's called for the tank turret normal, and then for the tank body. It goes through these children and through these children as well. And once it doesn't have any more children, then these functions and all of the tree created by them goes up and up and up until it ends and the function eventually stops. So basically this is the logic for this one. Other than this, of course, we do have onDestroyed, and as you see here, we get the HP system. And the HP system has this nice signal onDestroyed, which gets triggered when the HP system detects that the object that it's monitoring is finished, is done. onDestroyed here gets called. Of course, we remove it, but before this, we also remove the camera from the camera manager because we cannot allow the player to change the camera to an invalid camera. And here also the UI gets the show response screen, but this is just more visual stuff. So basically this is what we have at the topmost level. One last line here that I mentioned that in onDestroyed the camera gets freed from the camera manager. Of course, the camera first, when the player gets instantiated, it needs to be registered to the camera manager. And this is the line that does this. So basically it tells the camera manager that's in the environment, hey, add new camera, and basically it adds this player camera. And the camera manager basically has a list of cameras, and the player can cycle through that list and choose the current camera via using the C button. By the way, all of the buttons are assigned in project, input map, and here are all of the possibilities. So move up, move down, left, right, fire, right mouse, change camera, and hide all. Don't worry about the camera, it will respawn when the player gets respawned, and it will call this again, so you don't have to worry about that. Now let's move to the next script, which is the camera script. And in here, most of the code, if not all of it, and actually it's all of it, is responsible for shaking the camera when a projectile hits the ground or hits the player or hits an obstacle. So basically this is a shaking algorithm. What it does, it just moves the offsets of the camera so that, for example, I'm going to use the second camera so that I can show you. So if I do the preview and I do the H offset and the V offset, you see it moves the parameters like this, so the player will experience kind of a shakiness of the camera. So nothing fancy, it's just this, it just shakes the camera when the projectile collision hits something. If you look into the tank mesh, we'll find the components of the tank, the turret and the body. They contain the 3D meshes that make the tank up. Besides the meshes, there are two other components that need to be there. First, there is the fire point, and second, there is the tank turret position. Let's discuss a little about the fire point. Basically, what the fire point does is just a position 3D node. It's nothing visual, but it tells where exactly the projectile should get spawned. So this is really important because the weapon manager needs to know where it should spawn the projectile, and it should not be the turret position, which, as you can see, it's here. So we don't want the projectile to be spawned here, it needs to be spawned here. And in some other cases, like some other turret types, we actually have more fire points, and the weapon manager responsible for that will actually cycle through each fire point and fire the projectiles accordingly. Lastly, we need the tank turret position to be specified on the body because the tank turret moves a lot separately from the body. And as one of the last steps of adjusting the turret to its new position is setting it up exactly on the body. Because as you see, the body also moves, so it's not really that hard to get them out of sync. And lastly, the collision shape is just a collision box, and this also gets adjusted in code because the tank body needs to be synchronized with the collision shape, and the collision shape needs to be the child of player body because this is the kinematic body. The animation player holds basically the animation of the turret moving, but here instead of moving the turret on the z-axis, we actually move just the parameter. And this is because, for example, if the turret has this position and it moves on the z-axis, it's not the local one, it will be the global one, and it will move like this. So to fix this, what I did was just a short here. It animates a parameter, and that parameter gets added to the correct turret direction. Now let's look at the systems that make the player work. And let's start with the mouse target because this one is the smallest. So in here, as you see, it's just 22 lines of code, so nothing special. But what it does here, it takes the current active camera. So regardless if it's the top-down camera or the player camera, gets referenced here. Basically what this script does is create a ray from the cursor on the screen to a position in the world, and then checks if there was an intersection. So we first need to get the mouse position, and we create a ray out of that one, and then we use the space state, which is a Godot functionality, to be able to intersect the ray. And if there was an intersection, then we need to put up the lookout position, and this one will be used to actually move the turret around. But there's also a debug functionality, and this is just a small target. It's invisible now, but if we added a mesh, let's say a cylinder mesh, it doesn't matter, and save it, we can see actually where the cursor points on the screen. So this is just for debug purposes, it doesn't have any use. Okay, now let's remove this because we don't want this functionality. So now let's head over to the weapon system. And what the weapon system does is basically, first it gathers input from the player, which is the left mouse button when it's clicked. It instantiates a projectile at the tip of the turret. It handles the cooling down or the reload rate, and also plays some animations and effects. Let's go into it and see how this all works. So the first thing that this script does when it initializes, it takes all the turret children and checks if they are fire points, basically if their name has fire point in their name. And this is because, as I mentioned, if the turret has multiple fire points, it will cycle through each one of them. And these are the two variables that will handle this. So the fire point is actually a list that will contain all the fire points, and the fire point index is basically a number telling which fire point should be fired at this moment. Next, we get the animation player, which is this one. So we need to go up 2 levels. So the first one would be systems and the second one would be player. And then we need to go into the player body and then the animation player. So this is how we get reference to an animation player. Of course, this is hard-coded, but since this won't change, it's fine. Next, we also hook the weapon cooldown timer. And the weapon cooldown timer is basically just a Godot timer that has specified a wait time and one shot. It doesn't auto start because we want to make sure when the weapon cooldown actually happens. In the process, which happens every single frame, we just need to check out if the fire was pressed, and if it was, then of course we need to actually fire the projectile. And what happens when we fire a projectile? Well, first we need to check if it's not actually cooling down, because if it is cooling down, we don't want to fire another projectile. Otherwise, the player can just spam the left mouse button and it will fire projectiles indefinitely. One thing here, the action just pressed, that means that it needs to be released. If we use is action pressed, then we can make this work just by holding the mouse button. So I don't have to actually release it. I can just hold it and the player will shoot at the fire rate that we specified in the timer, which is 0.5 seconds. Actually, this is better, so I leave it like this. So what happens when it's not cooling down? Well, two things happen. First, we instantiate a projectile and then we restart the cooling down functionality. So let's look at the instantiate projectile. So here we need to take the projectile prefab, which is specified here. So export variables are variables that are visible here. And the projectile prefab is just another different Godot scene that's being drag and drop from the file system into here. And we use instance to create a new instance of that projectile. Once we do this, the projectile is not actually in the scene. So by using getTree, root, getChild, we actually get the main scene root. And why don't we just add the child here? Well, we could add the child here and technically it should work. But just to make sure, it's better to add it at the root level because of the transforms and the position, and we have a deep hierarchy of nodes. If one node changes the position, for example, when the developer moves the player like this, well, the whole hierarchy inside will actually get position changes because of this. So in order to avoid any kind of issues, we just add it to the main root so that we know that 0 is always 0. And vector 3.0 is always 0, 0, 0. Next, we get the current fire point. And as I mentioned, the fire point index cycles through all the fire points. And we need to do the cycling as well. So of course, we actually increase the fire point index only if we have multiple fire points. And then if it reaches the fire point position, that means the last one, then we need to go back to 0 and then restart the counting from the beginning. So once we have this in place, we can properly initialize the projectile. And the projectile initialization has multiple steps. Of course, we need the current fire point, which will give the projectile its initial position and rotation. It will also give the lookout position, which is the mouse target. And this is important because the projectile needs to be aimed at this position. The damage can be specified at the projectile level, but it can also be specified at the player level for simplicity. So if you have multiple objects that get instantiated in the player, if you put it up to the player level, then it's easier to customize everything inside. Next, we also specify the color of the projectile, and since we know this functionality is just for the player, we can hard code it to green team color because the player is green. And lastly, we get the player body, which is the kinematic object, and this is important because we want to avoid the collision from the projectile to the actual player. So by checking for the collisions with the parent and removing them from the beginning. Lastly, in this function, we do a smoke and a muzzle effect, and those two are just visual effects. And they spawn at the current fire point and the current fire point origin. So basically nothing special, just the VFX manager handling some nice VFX for us. Next, we have the start cooling down. And the start cooling down is basically a variable that tells, okay, now it's cooling down. Then we do a random number generator, and this is just to make it a little different every single time. So this actual wait time doesn't matter because we specify the cooldown from 0.35 seconds to 0.75 seconds, and we do a random between them, and then we start the cooldown with that value in place. Of course, we also play the animation turret fire. This could happen at any point, of course not before this, but here should be also fine to be played. And basically, these are the functionalities that make up the weapon system handling the shooting for the player. Now that we know how the targeting and the firing works, let's have a look at how the player moves. To do this, we need to head over to the player mover. And this one is a little big, but don't worry, because it's very nicely separated to be easily accessible for everyone interested in finding out more how the player moves. But before we dive deep into it, we need to understand what are the exact functionalities of this script. First, it moves the tank up, down, left, and right. And please note that these are not up, down, left, or right for the tank, but from the perspective of 45 degrees. You'll understand what this means a little later when we actually see the code. It also applies the gravity. In this case, it's not really necessary because the whole thing is flat, but it does apply gravity, so in case your terrain has hills or valleys, it will work as good as on the flat one. It also rotates the turret towards the mouse intersection in the world from the mouse targeting system, and also applies some nice rotations when the tank fires. They are not important functionality wise, but they are important visual wise for the player to actually feel the power when the tank actually fires. So here we just get some parameters in the ready, but everything gets processed in the physics process, and it's nicely put in different functions, and we'll go into each one of them and see how it works. So first we need to process the direction and get it into this here vector. And the direction is basically where the tank is headed if the player presses one of the following keys: move up, down, left, or right, specified in the player input in the configuration. So here the tank doesn't move forward, back from its own position, but rather if we go to the demo scene and we go to the camera, you can see that here's the tank. So it moves up from the screen, down from the screen, left and right. And these adjustments are actually made in code like this. So for example, if we move up, it's a combination between vector left and vector back divided by 2. What gets returned by this process direction is a normalized vector, and that means the vector of length 1, specifying the direction, or 0 if the player doesn't press any key, where the tank should move next. We need to process the turret, and this one does the turret rotation towards the target position. Let's look how this happens. So first we get the target position, and as I mentioned, we get the mouse target, and is this one. We actually could have gotten it from the code since we have look at position. So instead of getting the target, we could just get the mouse target and the value look at position. And this is actually better. So I'm gonna fix this right now. And why is this better? Well, it's because this is mostly for debugging purposes. And if you say, okay, now I'm removing the debug stuff and this gets removed, then this won't work anymore. So it's really important to make it work without the debug as well as with the debug functionality. We need to preserve the scale of the turret. And this is important because all of the transforms, that means the position, the rotation, and the scale do happen when using different functions on transform, and sometimes the scale might also get messed up. So we need to preserve it and then reapply it a little later. So first we preserve it and then we generate a new transform. So it's not actually, we don't use the look at, we use looking at, which will actually give the new transform to the target position. And this is important because I'm using this interpolate with, which makes the turret move slowly or smoothly towards the final rotation instead of directly moving to that particular position. And this gives a nice feel for the player. Once this is finished, of course, we reapply the scale and also unwanted rotations because, for example, if we remove one of these and we point close to the tank, the turret will also point down. So we might avoid this, but in case your game has hills and the turret needs to rotate up or down, you might want to remove these rotations, or at least the one that handles up and down movement, so that the turret can properly rotate. The other one will tilt the turret, so it should always be 0 because the turret cannot possibly tilt. Okay, lastly here, once we set up the look at position, as I mentioned in the tank mesh, we have the tank turret position, which needs to be synchronized as the final turret position. So we need to set that in place. This is the final turret position. But on top of this, we also have getting the turret forward vector, which is this long line, and multiply this by the turret animation forward. And this is the value that gets animated by the animation player. And originally it's just 0. So all of this is not used. So the turret gets positioned right on top of the tank body. But when the turret actually fires, then the small animation gets played. So this value changes from 0 to 1. So the turret slightly moves back and forth. So if we quickly play it, you see that the turret doesn't move forward or back. But if we fire, the turret starts moving forward and back. So this happens because of this line. So now that we have the turret rotation, we can move to the tank rotation as well. So the tank rotation, what does it do? It basically rotates the tank's body. So not the whole thing, it just rotates the tank mesh, and this part just the tank body from the tank mesh, because as I said, the turret rotates separately and we don't want to get involved in the player body because some other systems are here. So when does this rotation happen? Of course, we need to make sure that the direction vector is actually a length of greater than 0, because if it's 0, then that means the player didn't press any key. And if a key was pressed, then a direction is either up, down, left, or right relative to the tank. And the player body needs to look at that new position. And we do the same as with the turret. So we use looking at to generate a new transform. And then we do nice interpolation of that with 2.5 multiplied by delta. This will assure a nice smooth rotation. Of course, you can change this value to make it rotate faster or slower. Of course, to reset the Z rotation to make sure that the tank doesn't rotate up or down as well. So if we play this, if you look closely at the tank body, if I press up, it doesn't move directly. It moves with a certain rotation speed. You see how the tank body moves? It moves so smoothly because of that interpolation. So if you change the value from 2.5 to another one, it will move either slow or fast based on that. So this doesn't actually move the player, it just rotates the tank body. The player movement happens in the next function. So here, if we go back, this was the tank body rotation, and the move tank is actually what moves the tank. So here, of course, you know the drill. If the length of the direction is greater than 0, then this means we actually have movement. And this means we actually have a velocity. And I don't want the velocity to be instantaneously fast or slow. So for this, I actually opted for acceleration and friction. So what it does, it linearly interpolates. What the interpolation does, it takes the current velocity value, which in this case should be 0, and the maximum speed, the direction times speed. And the acceleration is what we are multiplying with at every frame to get that velocity to that point. So basically with this, the tank will accelerate to its maximum speed. which is the speed. If there's no key press, then it will decelerate with friction. Of course, you could have used acceleration, but that would have been weird because, as you know, a car might accelerate at different rate as it slows down with the friction. Of course, velocity on the y-axis is always -15 or whatever gravity you want to put into this. And lastly, we use the move and slide functionality from Godot, and here we specify the velocity that we just calculated. So this is just a vector tree with its x and z components based on the direction and the y component based on the gravity. And also we need the up vector here. So this will handle the tank movement. And lastly, we have the reposition collision shape. And what this does is actually move and rotate the collision shape to fit the new player position. Why is this relevant? Well, let's see. If I comment this line and I use debug visible collision shapes, press F5, and as you see, the collision shape is okay right now. But if I move it like this, oh, the collision shape is not anymore okay. So if we go through objects, you see that the tank goes through buildings because the collision shape is basically wrong. So if I decomment this back, and now we can see that the collision shape nicely moves with the tank. So this is the behavior that we are looking for. So how does the reposition collision shape work? Well, we simply put the new origin of the collision shape to the player tank body origin, and then we move it slightly on the forward vector. So please note that the forward vector is this with minus, so I'm just putting the minus here in this case. And this is not divide, this is just to go to the next line, because we add this also on the y-axis, because otherwise the collision will go through the floor and we need to be careful it doesn't do that. We also need to sync the rotation, so this is this line 4, and this is what makes the collision shape synchronize correctly with the tank body. And lastly, we do have the helper functionality, which checks if the turret is on a tank side or the other, and this was responsible for the tank body rotation. So this is actually for visual purposes. This is why I haven't been into this before. But what this does, it checks if it's on one side. So this is the X or minus X. So basically left or right side. And if it's the one or the other, then it gets tank body rotate, which is also a value that gets changed by the animator when the firing sequence happens. And it rotates the tank body like this or like this. So how does this work quickly? Well, it's a little complex, but I'm gonna quickly show it. So first it takes the tank body position, and then we get the target, which is the tank turret position. And then we get the forward vector of the tank turret. So basically this means where the tank turret is pointing towards. So now we have a position forward from the tank turret and the current position. And this will give us the difference vector. So basically this is just a vector from the tank origin to where the turret is pointing towards, multiplied 5. And of course you need to normalize this. And if we use the dot product, and this is a nice functionality for Godot, because the dot product will be 0 for a straight angle and greater than 0 for angles narrower than 90 degrees and lower for wider angles. So we can check this dot product result of the difference vector to see if it's between an angle or not. And what this does in practice is that, for example, the angle now is a position that we want, but as we move inside, you'll see, oh, the animation stopped. So here it's where the angle for this side stopped. And then if I move, now the animation started. So this is basically the value that you're calculating. So this one is the value. And if the normal, that the product, the value, this one is within the range, then it will give us the result we wanted. If not, nothing will happen. So basically this is what this function does as well. So this is the player functionality. I hope you liked it. It's a little big and some of it is just for polishing, so it's not for functionality, but do remember that in finalized game products, this is super important. So make sure that your game has visual effects like these. This is it for this video. Let's discuss about tank projectiles. And when discussing about tank projectiles, there are two parts involved. The first one is, of course, the projectile. The second one is the means of creating and firing the projectiles, or in game terms, the weapon system. Let's look at the three different projectile types present in this project. So the projectiles that we are going to look at are the main projectile, which is a linear projectile. It moves straight forward. We're going to look at the rocket, which has a different trajectory, and an arc projectile, which is basically a cannonball, which moves up and then comes down in an arc. Each projectile has, as you probably noticed, its own scene with its own parameters, objects, and scripts. Let's get started with projectile 1. And as you can see here, right out of the bat, all the projectiles kind of have the same scene structure. So once you'll go through one, you'll understand for all of them. So what does it have here? Of course, it has the projectile model, which is just a 3D object. This one I created in Blender, but in the rocket case, I created in Godot directly. We also have a timer. This is just a Godot timer that acts as the time span of the projectile. We do need this because in the case that the projectile hasn't collided with anything and has exited the main scene, so that means that the projectile is still around but it cannot ever go away, we need to kill it at some point, and the kill time is 2 seconds. We also have a trail, which is a component from the trail system. This is a very nice plugin, which I recommend for Godot. This makes awesome trails. And the collision, which is an area collision. And here we have a collision shape, which should match our projectile if we want our projectile to be precise. Here I want to point out that the collision here, the collision layer doesn't matter so much because you don't really want the projectile colliding with themselves. But we want the masks to be 1 and 2 because on 1 we have the tanks and on 2 we have the buildings. So the mask is what the projectile interacts with. So this is what we actually need from it. So let's look at the code. This is the projectile code. What we have here is, of course, the speed and damage, and these values are exported so we can change them at project level. So this is quite neat functionality. We have the process functionality, and this is the easiest one for this projectile because once the projectile is enabled, because if it's not enabled, then it will just return, so nothing will happen. We just translate it forward using the current speed and the delta, which is the time between frames, so that this is frame rate adjusted. It won't move at different speeds if you have 120 frames per second or 60 frames per second. The initialize function is probably the biggest one. And one important thing that I want to note here is the fact that these parameters and this method is the same for every single projectile. And this is important because if we keep the same header and the same parameters, then we can just swap the projectiles in and out, and we don't have to put more code to handle each projectile type. Because as you'll see here, some parameters, like the target point, is not actually used for this projectile. And in other cases, it will be used. But you'll see when the projectile gets called, it's just one line, and it will work for every projectile. So in this case, we need some parameters that might not be used by one or another projectile. What we have here is the start point, which tells where the projectile should start from. The target point, which is actually not that important for a projectile that moves indefinitely forward. This is more for projectile that target a specific position. The damage of the projectile, the color, which is mostly the color of the parent tank object, which is basically needed to detect collisions and basically avoid collisions with the parent, and the parent script, which has specific functionality just for arc projectiles, so this won't be used in this one as well. So first we need to set up the rotation
So this is how we set up the projectile rotation to the fire point rotation from the tank. Then we set up the position. So as you see, the start point is basically just a transform that contains rotation and position. This is enabled. It happens here because if we don't put this, then when we instantiate the projectile and it initially gets instantiated at position 000, I think, we don't want the projectile to actually start moving from that point. We want the projectile start moving once it gets the right position. So we first set up the right position, which should be the tip of the tank's turret, and then we enable it so that it moves from that position. We also set the time span to start, and we also need to change the color of the projectile. And here you'll see a familiar code if you checked the other tutorials. So we need to get the current material, duplicate it, because otherwise we will change all the projectiles and you don't want to change all the color just only for this one. And then we basically set it back to the same object. So as you see, this is basically the same line. So you take the material, duplicate it, and then set it back and then change its color. This will make sure that just this particular instance of the projectile gets its color changed. And there is another way to do this. I want to quickly mention, but I'll not be using that way. So for example, if we have a material, if you select this material, you can put in resource and local to scene. This will actually, in theory, work all the time to make this material local. I tried it. For some particular cases, it might not work. I might be wrong, but I'll be using the duplicate because that's like 100% sure that it's going to work. But this is another way to do it. I just want to mention it. So going back to the code, lastly, we have a tween. And this tween basically just interpolates the speed to not have the maximum speed from the beginning, to just have a small transition from the current speed. So the maximum speed is 10 in this case, and the current speed will be transitioned from 0 to the maximum speed with a factor of 0.25, of course, with a sign transition and is in and out. So if you want your speed to be directly that fast, either just remove the current speed and just use speed here and completely delete this tween, it won't matter. Next, we have the time span timeout. And as you can see, there's no code for this. So how does this gets connected? Well, it's because I'm using the functionality from here. So if you just click on the time span timer and node, and we see here a list of signals that this node triggers when they happen, and the timeout happens when this timer reaches 0. So I just used connect and then put on this script, and it generated this functionality. When the time span gets 0, then we free it from the memory. So basically we kill it. Next, we have the on area body entered, and this is important because the area can detect multiple collisions, but we actually just need to detect the body collisions. So for this, we go here and we use the body entered, and of course you do the same as with the timer, and this is what we end up with. So what happens here? First, we need to prevent the self-collision. So if the body that was detected is the same as with the parent, then we return, we don't care about it. The next one, if the body has node HP system, and if you have looked at the main player functionality, you know that HP system is right below the kinematic body, and this would not have been possible by this. Otherwise, I would have to go up one level, actually go up 2 levels, and then go to systems, and then go to HP system. So this would have looked like. So it was kind of weird. It's much easier to put it like this, and it's much more clear. Of course, if it does have this node, then we take it out and call take damage, which takes the projectile damage. It's subtracted from the life. And also it informs the object that took damage which object damaged it. So this is important for later when the enemy gets hit by the player, and the enemy actually acquires the target from that hit, not from its other sensors. Next, we set up some nice effects, and that is a small explosion and the camera shake, and you can change these values to make it look more nicer. And lastly, we need to destroy the projectile, and we get this. So if you run it, this is what you get. The projectile instantiates an effect. It's quite cool, it's quite nice, it works nicely. You can change the values like damage, like speed, timeout. Of course, the projectile, once it leaves the space, it will actually die by itself. So you see it disappears, so that's the timeout. That's when it disappears. If you want your projectiles not to disappear from the screen, there are two ways to do it. Either you go to the maximum length and you try it like this, and then you adjust the timeout. The other one is completely remove the timeout and surround the scene with some colliders, and basically you're assured that the projectile, even if it leaves the scene, it will eventually collide with something and it will get destroyed. So both are valid options. You can pick whatever you want. Now let's look at the rocket projectile. And before we look at in the rocket projectile, I'm going to quickly show you how you can actually change projectiles and in the player. So I'm going into the player quickly and then to the weapon system. And here, as you see, we have the projectile. So if I just drag and drop the rocket projectile, and then of course I need to save it. And so this is the rocket projectile. Its main difference than the regular one is that it actually aims for a particular target. So it doesn't move aimlessly towards infinity, but actually aims to a particular target. And the other part is that it starts with a particular rotation and it tries to adjust that rotation to eventually arrive at the target position. So how does this happen? Let's look now at the projectile rocket. So in the projectile rocket, we have the mesh, which is just the 3D model. We have the collision shape, and this was required because if you don't have it, then the kinematic body will complain. But the actual collision shape that matters is in the area. So here the area gets actually on area body entered, similar as the other one. We have also the time span and the nice trail effect. Let's look at the code now. So here, as you see, the initialize is basically the same, but the main difference is that we just put the origin position. So we just put the initial position. We don't put the rotation because the rotation actually is randomized. So the projectile starts with a random rotation, and basically this twin is the same. So it adjusts the speed to not be instantaneously fast from the beginning. In the process, it's different because it calculates a direction from the target point that we want to achieve to the point that we are currently at. So this is a vector. We need to get the length of it, and then we normalize it to length 1. And if the length of the vector is below 2, then this means that the projectile is close to the target and we can actually delete it. But what makes the projectile work is actually we translate it to the direction multiplied with the current speed and the delta. So as I mentioned, the direction is a vector from the final position that we want to achieve to the position that we currently are at. And we need to translate it slowly to the final position. And of course, if we just use this, then the projectile will look kind of weird. So I'm going to quickly change this. So I'm going to play this because it will be interesting. The projectile will still go at the destination, but I don't know if you see it. The projectile doesn't rotate correctly. And basically, this is what the look at does, because this is basically a name that I came up with. Takes the previous position. So I'm going to show you. This is the tank, and this is the position that we want to arrive at the end. So the projectile will get fired, let's say, with this direction, and needs to eventually go to this position. First, the direction, so from the target point to the projectile, will be this one. So this vector will actually make sure that every single frame, the projectile gets adjusted accordingly. Now, to actually make sure that the projectile gets this kind of rotation, instead of this one, because this will look weird, right? So we need to avoid making it like this and make it look like this. So how can we do this? Let's take another arc because it's easier to see. So we take the previous position, which is this one, and the current position, which is this one. So these are the two positions. So we have the current position minus the previous position, and this will actually give us this small vector. And using this small vector, we actually look at, so we use the mesh to look at this vector multiplied by 10, which will be this position. So basically, the projectile will look at, so in this case, it will look at this position, this will look at this position, this will look at this position, and so on and so forth. But it will make it look like it's moving the right way. Basically, this is called a tangent, and this is basically a line that's tangent to a circle. So I think there are other math operations to do this, but this is what I came up with and it works nicely. But we need the previous position as well to make this work. So basically this is how this projectile rotates nicely. And of course, when the collision happens, then this code is the same as the one in the previous projectile. It checks the collision with the parent. It checks if it has an HP system, and if it does, then it takes damage. And also it has explosion and the shake camera. By the way, this value could have been exported nicely so that it could have been changed like at the Spectre level. But yeah, you can do this in your own project. Now let's set up the last projectile to the player and see how this works. So one important thing is not only that the projectiles have the same initialize function, it's also important that with the same functionality like pointing to the right target, it makes the projectiles work in any case. So this projectile, as you see, it forms an arc, so it can go over buildings or over obstacles. So this is more for an artillery purposed object. So how does this work? Well, let's look into it right now. So the arc projectile has the same functionalities as the one before, with the exception that the damage area is actually a sphere, and mostly the artillery projectiles do splash damage, so you can increase the sphere size if that's what you want. Now let's look at the code, and here in the initialize, I said it's the same for everyone. We need to set up the position and the rotation to the correct ones from the fire point, and then we do the arc calculation. And basically what this does is actually broken down into two parts. First, we calculate a vector that is how much force we need to apply to this projectile in order to arrive at the correct final destination where our mouse cursor pointed at. And the second one, we actually need to apply this to the physics enabled object. And as you can see, this object is actually the only projectile that has a rigid body. And this is really needed because otherwise we cannot make it work. First, we need the arc height, and we calculate the velocity. And the velocity, as I mentioned, is a vector that actually stores how much power we need to apply in order to arrive at the correct destination. Arc velocity gets the position, it gets the final position, it gets the arc height, which is the actual height of the arc, how much we want it to go up, and then the gravity. And you'll see here some small values that I modified, and this is because the initial values didn't work properly, so I had to adjust them a little to make sure that it reaches the correct destination. And then the arc velocity, basically we calculate the velocity using a displacement. So here some math is involved, but the end result is basically a vector that has three components, and the final velocity still needs some little adjustments. So we do need to modify the up vector a little, and then the x and z one, and this will assure that the arc nicely arrives at the destination. So once this happens, the last thing we do is add the central force, which is the final velocity. We also set up the material for this projectile to reflect the color of the parent. And the damage is similar to the previous one. The only difference here is that if the body doesn't have an HP system, then it's most likely a building or it's an empty space. So if this happens, this code is called. So what this does, it gets the reference to the parent script, and then it calls this on projectile miss. And this is important for the tank AI that handles artillery, because for example, if it goes behind a big building, let's say this one, because it can position itself here. And when it starts firing, it always goes into the building. So this is how it knows, I'm firing at the building and not hitting anything. So it will adjust position, still fire at the building, adjust position again, still fire at the building, adjust again, until eventually it goes past the building. So this is how this artillery tank unit gets information about if the projectile hit the correct target or not. This is important for just this projectile, and the time span, which is similar to every other projectile. This is the last projectile. I hope you enjoyed this section. I'm gonna change the projectile of the player back to the projectile 1. By the way, this is how you can change the projectiles for the enemy as well. Next, we'll go into other parts of the project. The sensors. Each sensor implementation is found in the course modules in the sensors section. Here I want to focus on how we can actually use them in a real life use case. Here is the sensor manager. So the sensors, or the sensor manager, is basically a collection of all the sensors that will be applied on each enemy to be able to use one or more to detect its targets. The sensor manager is meant to be used as a module component containing other module components. So you can either use individual sensors on their own, like range detector, field of view, so on and so forth. And you can also use the sensor manager if you want the power of more sensors combined. Basically, the sensor manager has these sensors attached to it and also a timer, which is the pole sensor timer. And if you look at the script, there are a couple of things that happen here that are really important for us. So first I want to mention this signal. So this is how the sensor manager informs other objects that, hey, my target list got changed because some of my sensors detected or stopped detecting some particular objects. And here are some parameters like is using field of view, is using raycast, so on and so forth. In the initialization is one of the new styles, and basically it's a key pair value dictionary called params. And here for each value we have an enum, and it will say if it should use field of view, if it should use raycast, and then putting those values from the dictionary to the actual variables in this part. Next we have the timer, and this time the timer is connected via code. So instead of going here node timeout, I opted for the code version. Basically, in theory, you should always use the code one because you have everything in the code and it's much easier to manage, because if some parts are not in the code, you'll find it harder to know what exactly is where. So this is why I put it here. Then we initialize the range detector and the raycast detector. In the process, there is one more thing that happens. So since the sensors actually, if we look at an AI, the sensors are actually placed in the non-moving part of the enemy AI. And this means that the sensor manager doesn't move with the actual tank. So to fix this, we update it at every frame to the tank position. So this will make sure that the range gets applied from the tank origin as well as the other sensors. So what happens when the timer gets 0? By the way, the pole sensor timeout is specified to auto start and not one shot. So it happens all the time with a refresh rate of 0.25 seconds. So we will have a final list, which is basically a list of the targets detected by the range detector. So these are all the objects around the enemy. Now, if this sensor manager is using field of view, then we will generate a new list, which is the field of view target list. And this list will actually be combined with the list from the range detector, because the field of view actually works infinitely in that particular range. So we might detect objects beyond the range. In order to combine these, what we will do instead is go through every object from the final list, which is basically what was detected by the range. And if that object is inside the field of view, then we add it to the new list. And once this is done, then we move the field of view list to the final list. And basically now we'll have the objects from the combined range with field of view. In the case we want to use raycast, so if there are objects occluding the enemy, so if the target is in the range, is in field of view, but it's behind a cube, let's say, it won't be detected if you use raycast, but it will be detected if you just use field of view and range. So how we can fix this? Of course, we go through the final list, which now either contains just the targets in range. So this means that either, like, let's say a target is behind the enemy but occluded by a cube, or if it uses field of view, only the targets in front of the enemy. But it doesn't matter because we can use any combination, so we can use it with field of view or with just raycast or with both. So we have the final list, and then if the target is visible, so this actually creates a raycast from the tank to the enemy, and if the raycast actually hits the target and not some other object, then it will append to the list. and then the Raycast list will get in the final version of the list. And once we have the final version, we can throw the signal out that the list was updated and give the final list to what system actually needs it to make the next steps. So this is highly customizable because it allows detection just the range or any combination range, field of view, and Raycast. Of course, some functionalities do require to be used in other ways, such as is target visible, so that means for the Raycast detector. This one is actually called in some other parts of the code when we already have the target and we don't see it at some point. Then this is kind of useful. Or the target is in range, kind of similar, or all the targets in range, just the range detector. So basically, these functions are just wrappers on top of specific sensors functionalities. These are useful in particular cases of our AI implementation, but the most useful is the signal on target list updated. Basically, this is the sensor manager. You'll find it in every AI system, so is the first one, is the sensor manager. It gets used quite heavily because this is how the enemy detects anything. So if we just play this scene, and I'm gonna use the debug sensors, and of course, I'm gonna spawn an enemy. So this is the range. And this is the Raycast. So I'm gonna put the camera. So if I move here, now the target is not visible anymore from their perspective. But wait a second, now they follow. Oh, now it's visible. So this was the last position where the target was found. And of course, it checks it a little. So this is the final result of the sensors. And you can customize them in the enemy initialization. It's not for this particular video, but yeah, it's in every enemy to be initialized. I hope you enjoyed it and see you in the next one. Let's now look at the HP system. You'll find this system in the demo folder, prefabs, systems, HP system. The HP system is a critical part of the project. It allows objects to have life and get destroyed if they take enough damage. Most of the code here is actually to update the health bar associated with it. And all of the children objects here handle the health bar, the health healing effect, the last hit timer, which when it will get triggered, it will regenerate health, and the health regeneration animation. So functionality wise, HP system has two important features, the maximum HP and the current HP. When take damage is called, so this is the most important function, because when take damage is called, then we need to subtract the amount from the current HP. And if it reaches 0, so if the current HP reaches 0 for the first time, we can check if it reaches 0, but we don't know if it's the first time. So this is what is alive is for, because if it's the first time, then is alive is true, and then it gets false, and then it won't be true for the next time the current HP gets below 0. And the HP system actually has two signals, on damage taken and on destroyed. When it gets hit, on damage taken happens, and this is important for the enemies when they get hit by the player to actually acquire the target. And on when destroyed happens, this is important because we need to actually destroy the object, but we don't want it to be destroyed here in HP system because there are some other steps that need to be taken to destroy other objects. So it's important to get the signal and then use it for later purposes. The other main functionality of the HP system is regenerating health. As you can see here, if the HP system receives damage, the last hit timer gets reset. Once the last hit timer is 0, then the should heal variable is set to true. And this means that from this moment on, the HP will heal itself. So how is this happening? So at every frame, if should heal is true, then the current HP gets added the heal factor times delta. And if the current HP is equals or more than maximum HP, we set it to maximum HP. And then the animation player stops the animation. This is just an animation that sets everything to 0. And of course, it updates the UI. So the UI is basically this bar, which is actually a gradient that has two values. I'll quickly show you what it does. So first we get the gradient from this one and we set the offsets of this one. But when update HP UI happens, it sets the two colors. So the first one with index 0 is red, and then the green one, because First we have everything green, so the red will start from the left, but it will start from nothing. And then we set the offsets of these. So if the player or the enemy gets more and more damage, this will change. So I'll quickly show you. So this is the red, it has like nothing happening. But once it starts taking damage, the offsets move. So red is more than green now. If I go far away, then at some point my healing will kick in. So this is the healing animation. It's just basically fade in, fade out for that background. But it will actually slowly heal me. And this can be tweaked here at the heal factor. So you can adjust it as much as you want. Lastly, what I want to mention is that this system is meant to be integrated below the kinematic body of either the player or the enemy. And this is needed because once this object gets detected from the projectile collision, they will ask for the HP system directly. So it's important for the HP system to be here. Otherwise, if the hierarchy were different for the player and the enemy, then it would have been a mess of a code to make everything work. So this is why it's important that the HP system is a child of the object that takes the collision directly. Basically, this is the HP system. I hope you liked it, and leave me a comment if you did.
The enemy topic is quite big. To tackle this, it's best to split it up in different functionalities. In this video, we will look into the enemy scene structure as well as the main script powering all the enemies. Let's begin with the scene. And if you check the main player functionality, you'll notice the resemblance. We have a dynamic part, which is the tank, and a static one, which is the systems and the finite state machine. The dynamic one consists of the tank's kinematic body, while the static one, basically the one that doesn't move, has all the systems that are responsible for various functionalities, as well as the finite state machine controllers. Looking inside the tank, we can find the actual 3D mesh, its collision shape that is required by the kinematic body, and we have two systems here, the communicator and the HP system, that need to be here because they are called when a collision happens, and the collision happens with this kinematic body. And this is why we have them here, because it's easier to use and we have a similar structure with the player. Inside the tank mesh, we have two important functionalities that are extra besides the 3D stuff. In the tank turret, we have a fire point or multiple fire points. Basically, from this is what the actual instantiated projectile spawns from. And in some cases, if the turret has multiple points that can spawn projectiles, we can have many, and the enemy script will actually cycle through every fire point. So that's really cool system. And the other part is in the tank body. We have the tank turret position. This is very similar to the player's tank turret position. And this will be used to synchronize the turret's position with the position where it should be on the tank body. This is mostly useful when we will be animating the turret from the recoil animation. Now let's continue with the systems. And in the systems, we have the following. We have the sensor manager that handles all the tank's sensors such as range, field of view, Raycast. We also have the tank mover, which handles the movement of the tank using a specified list of 3D points. We also have the target handler, which is basically another layer on top of the sensor manager to actually manage the target and to check if one target is visible or not. And we also have the cover handler, which handles the cover functionality of mostly the retreat finite state machine, but also in the case of the defensive tank, the attack state. And lastly, we have the finite state machine states that are patrol, attack, and retreat. They both have their own unique scripts. And we also have the state machine player, which contains a unique state machine for each type of the tank: aggressive, defensive, and tactical. Let's get into the main enemy script, which you'll be looking in this particular video. And this script is big, but don't worry. Most of it just initializes systems and changes color. Let's look at how. First, we are greeted by a long list of export variables, and these variables actually handle exposing these at the inspector level.
This is easier to use when iterating through various numbers or for people that don't know how to code and are more towards game design. These are important because you can customize all the tank instances using the same parameters. Next, we do have some components, but in the ready function or the initialize function that is called once the enemy gets instantiated, we have a lot of stuff going on. Here, there are a couple of things that I want to point out. Both the enemies and the player have the meta tag type, either enemy or player. We have some more initialization here, either done by using the $sign or by getting the node path. So both of these are valid in Godot. Here we initialize the color of the tank. We'll go through it in a second. And from this point forward, we have a lot of systems. So we have the finite state machine, we have the tank mover, the HP system, the sensor manager, target handler, and so on and so forth. So most of these are very, very similar. What is important, and I should mention, is that some of them do require more parameters or require references to other systems, and others require less information. So in order to do this, I had two options. The first one that I used initially was to have all the parameters specified in the initialize function. But that turned out to be not ideal because the parameters will increase or will decrease or will change position and so on and so forth. I found a better way to do it. Basically, the initialize of every system gets a dictionary with key pair values. And the key is the parameter while the value is the actual value of the parameter. To know exactly what keys go where, in each system, I've created an enum called params that contains what components this particular system needs. So for example, in the case of the sensor, we do have some variables like should use a field of view, should use Raycast, a reference to the parent, a detection range, and the tank object. So here we have multiple things, either just some values or some other systems or even references to this particular script. And of course, some are bigger, some are smaller, depending on what other systems they need to use. Some systems, such as the HP system or the target handler, do have callbacks. For example, we hook up to on damage taken and on destroyed from the HP system. Basically, these are functions that are called either when a projectile has been registered hit on this enemy, or even if the enemy was killed by having its HP less or equals to 0. And there are some other callbacks that we can find here, but basically most of this is initialization. In the process function that happens every single frame, we set a parameter for the finite state machine. And by the way, this is how we provide parameters to the finite state machine. We call set parameter. And instead of having them written down, I've opted to use globals. So in globals, you'll find a list of all the parameters that can be used in the state machine. This is also to avoid mistakes of typing, of just having like a typo and nothing works anymore. And also I have the states of a state machine coded here so that no longer need to hard code it when we actually want to reference a particular state. And in this case, it's the retreat, and the retreat percentage is a number basically saying how much percentage of the life should be remaining before you can actually trigger the retreat. And I think for the aggressive AI, it's below 20%. The start function is important as the enemy instance first needs to get created, initialized, and then to start actually executing the finite state machine. This function assures that the finite state machine doesn't have its enabled parameter until everything is ready to not create possible messes. So the state machine will actually don't do anything before this start is called, because the enemy I will get instantiated at the 000 and we need to move it first to a different position, and then from that on start calculating what's the path to the patrol point or where the enemy is actually in range of the specified position or not. So this is critical to have this function. The next two functions are about changing the color. And here I have two important things. So first, we create a material called highlight material, and we call change material to the root node of the tank mesh. And this is actually a recursive function, which we'll see just in a second. But basically what this does is goes through every element, every child of this one. And if the child is a mesh instance, then it will change its first material to this specified one. Of course, after all of these meshes got the new material, material, then we can pick the color corresponding to the theme, then we can apply that color to the highlight material. And let's quickly check the change material. It gets the current node and the material, and then it takes all the children. So if you go into the tank mesh, it gets the tank turret and the tank body. Since those are not actually mesh instances but just spatials, they go inside, and here is that normal mesh. It actually will go inside of this one, and then here is this one, which is the mesh instance, and it will change the material for this particular one. So this is how this change material works. And there's a small hack here, because for this particular object I've set up the material in Blender for the second position, so it was actually a problem, but in your use case you might just remove this and it should work just fine. Of course, for every node we need to call back change material, but with this particular child node, and this will actually stop executing once no child is found. So basically, if it reaches, let's say, really a deep down node like tank body, after this was parsed, then it will get the child nodes. This will be a list of 0 elements, and it will no longer call change material. So basically, this is how the change material recursive function works, and it nicely changes everything. An alternative to this would be just to change material for every single object that makes the mesh, but that would have been a task that is actually time consuming, because if the mesh changes in any way, then we have to hard code every single mesh that's inside and make sure that we covered everything. So basically this solves this problem. The other two functions are called by the state machine player, and they are the following. In update is called at every single frame based on the state. If it's patrol, attack, or retreat, we actually call on update there. So instead of process, which if we use process in all of these states, they will get called at the same time. So it will be like the tank patrols, attacks, and retreats at the same time. By using this, we actually make sure that on update gets called only when the state machine actually plays the current state. So this is really important. In some cases, we don't actually run or need to run a particular state every frame to use its benefits. We just need when on a state is entered or left, and call specific initialize function or remove objects or destroy objects if the state was left. So on state machine enter, we have both sides of the transition, the state that the transition is from to the state that where the transition is to. And of course, in the from state, we'll call on leave. That happens only once, so it's used for de-initializing stuff. And on the other side, we have on entry for states, for example, the fire state in the AI. We actually need to call it once and then change it to cooldown or reload state. This is actually what's going to happen. We don't need to use the update every frame. The last parts of these scripts are actually callbacks of various systems that we used in the initialize. So for example, on damage taken is actually called by the HP system, and it's used to inform the target handler system to set the target externally. So basically, if the current AI instance doesn't detect the player because it's not in any sensor range, but the player hits this target, then we don't want this to be a sitting duck and not retaliate in any way. So for this, we actually call on damage taken and we set up the target. So it will follow the target and seek to kill. Also, by the HP system, we have on destroyed, which needs to do a little cleanup. We first need to clean up the patrol, which is basically the finite state machine for patrolling purposes, and this one hooks to a waypoint system, and we need to free that so that other tanks can be able to use this particular waypoint system. We also will instantiate an explosion. This is a nice effect. It's by the VFX manager. And we need to unregister the instance from the tank debug. This is the tank debug that you can see on top left if you enable the debug mode. Lastly, after all of this, we can safely remove the object because this object no longer has any references to the scene. On target found is called by the target handler, and this is responsible to inform the state machine that a target was found. So in the state machine, we set this up to has target to true. Alternatively, when the target is lost is also a signal received by the target handler, and it will inform the state machine that there is no longer any target. On signal hit is called by the communicator signal, and this is basically just a small object that is instantiated by one tank that detected the player, and it's sent to a tank that hasn't detected the player yet. So basically what this does is receives this signal, and if the target is still valid, like it's not destroyed by other enemies, then the target handler will also acquire this target externally. So this is used to communicate between different AI systems. If you want to know more about the communication, you should check the communication system video. This is it for the main AI functionality. Of course, this is the topmost script of all of this. We have different systems that we need to go through, and also the finite state machine states, which are basically finite state machines in their own particular rights. Let me know what you think about this in the comment section down below, and I'll see you in the next one. Let's look now at the enemy's tank mover system. This system is responsible for moving the tank across a list of steps. They are provided in the 3D space, so they are vector 3. Then the tank mover cycles through every single one of them and moves the tank accordingly. Let's find out how this system works. First, we need to initialize this, and as the enemy actually has the speed, we do need to provide the speed at the initialize step. And then we get the tank, which is the kinematic body, and also the tank mesh. We will need them both for our next steps. The main functionalities that are called in the tank mover are the following. Start move, which takes a list of steps and also initializes the index of the whole path to 0. Reset, which stops any movement that is currently happening. And also a query that will say true or false, either if the path is finished or not. Basically, if it's moving or not. So the actual movement happens in the physics process. First, if you don't have a path, and if it's null, then we don't actually care. But if you do have a path, we of course need to check if the index, so if the current position is not the final one. And if it's not the final one, then it means that we have to go to that particular one. We need to compute the direction. So in order to do this, we take the 3D position that was specified at the path index position and subtract the value of the tank's position. This will give us the direction vector, or the vector that is headed from the tank to that particular position. If the length of that direction vector is below 1, then that means the position was reached and we need to increase the path index. If it's bigger than 1, then this means we haven't reached yet the position. So we need to apply a translation, and of course you need to normalize the direction, because the direction would be the whole vector from the tank to the new position. By normalizing it, we take a vector of length 1, but the same orientation. And we multiply it with the move speed that we used in initialize, and also with the delta between frames, so we make sure that it's frame rate independent. Next, this handles the actual movement. But what about the rotation? We will use the tank mesh, as we don't want actually to rotate the kinematic body, we'll just rotate the 3D mesh. So what we do, we'll make it look at the next path, which is the path we're actually heading towards. Of course, we need to also reset the rotations that we don't need. This is to prevent the case when the tank gets closer to the position and the position actually gets below it, kind of. So it might be that if we use look at and we don't reset the X and Z rotation, the tank will look actually down and it will look strange. So make sure that this is in place. Of course, if you have terrain that's not flat, then you might need to change this, but I would rather go for a different route, let's say a Raycast, and check the terrain below and check the normal there. That's the other way to do it. And if the path index has reached the final position, then we emit the signal on finished moving. This will inform any particular objects that are subscribed to this notification to make sure that other functionalities are played. For example, if the enemy has reached the destination of a waypoint, then we need to make sure that we need to go to the next one, and so on and so forth. So basically, this is how the tank AI moves. By the way, this is just the movement functionality. The other part of the movement functionality is using the Navmesh to actually generate the path that's being provided here. So this just moves the tank. But you will see later on how we can also use the Navmesh to generate the path. I hope you enjoyed this, and see you in the next one. Let's look now at the waypoint manager and system. I'm going to play the scene quickly and spawn on AI. So when an AI gets spawned, they automatically go in the patrol mode. And if they find the waypoint system, then they'll move to the closest point, and then from that point, they'll do the whole waypoint step by step. Of course, at one point, only one AI instance can use a particular waypoint. Let's see how this all works in this lesson. This is the waypoint system. It might get confusing a little, so I'll try to make sure that everything is straightforward. I'll start here at the waypoint level, and the waypoint here is called waypoint system, but it's actually just a waypoint. And the waypoint is formed out of individual points, like these ones. These are just position 3Ds. And they specify where the tank should move next if it's following this particular waypoint system. And we have three scripts here. We have the waypoint manager, the waypoint system, and the waypoint node. To understand how they work, instead of going through each directly, let's figure out the steps how the AI actually uses this system. So the first contact with the waypoint is asking the waypoint manager, can you give me the closest waypoint node that is available? Available means that it's not actually used by another AI enemy. So if we go here into the waypoint manager, what we have here is, of course, in the initialize phase, we get all the waypoints that are children to it. So in this case, it's just waypoint A, but we could have easily made other waypoints as well. And here we have get closest available waypoint. So what this does, it goes through all the waypoints, and if it's in use, then it just skips it. And if it's not in use, then it means that it's free. And then inside of this, not only that we get the waypoint, but we also get the closest node from that particular waypoint. So if we look back in the scene, we have 4 nodes here. 1, 2, 3, 4. The closest node from the player would be this one. So usually, since most of the AIs get spawned here, they either get this one or this one as points. Going back, so you get the closest point. Of course, we don't know for sure if this particular waypoint has the closest node. We just know that this is the closest node from this waypoint. When we call the get closest node from the waypoint, we know is the closest from this particular waypoint. But if it has more waypoints, some closer nodes might be even more closer to the actual position that we are specifying here. So we need to make sure that we actually take care of this and we get the closest points. So to provide a better example, let's say I'll duplicate this and move it a little. So let's now say we have 2 waypoint systems. So waypoint 1 and waypoint 2. It will get the closest point from this one and from this one. And it will determine based on the position, let's say it's this one is the closest one. And if this one is free, then it will basically return this node to the player. So this is how this functionality works basically. So it just checks all the available waypoints that are not in use, and then returns the closest point for each. And then once the player decides, oh, this is the closest point to me, I'll use this one. So basically, this is what happens at this level and not much more. So the waypoint manager just knows all the possible waypoint systems and gives the closest available waypoint. Now, if you look one level down, we're at the waypoint level, is the waypoint system actually. Here we actually have the specification of the points. Every children of a waypoint system is actually a 3D position that the enemy needs to do in sequence. First, we get all of the children. In the process, we basically just display them with a debug line. So this is just for visual purposes, no functionality here. And in here, we do have 3 main functionalities. Get the closest node. This gets the node closest in this particular waypoint. So of course, it takes a position and then goes through all of the points here. And if it detects an even closer point, then it updates the closest node. And once the points are finished, the closest node is returned. This is only used in combination with the waypoint manager, because once the enemy AI has locked down on a particular waypoint and it moves to a particular position, then they will use the get next node. So this one works as following. It has a current node, which is specified here, and then it iterates through the list of waypoint nodes. And if we find the current waypoint in the list, then we know that the next one is where it should go next. And of course, you need to prevent, if it's the final point, we need to go to the first point. So basically, this is how we can loop a waypoint system with the movement. Lastly, we also need to trigger the waypoint use so that no other enemy can acquire this waypoint system. So this is actually called by the children. I mentioned this. It should not be called at this level because the waypoint manager will give the enemy a waypoint node, which is actually a position. And that waypoint node will trigger this one from the parent, and then that's basically it. The last level here is the waypoint node. If you go inside here, it's quite simple. It takes the parent as the waypoint system. It triggers the waypoint use from the parent, and it also gets the next node from the parent. So the waypoint system is actually an in-between component because get closest node is used by waypoint manager, get next node and trigger waypoint use are used by its children. So you as a developer don't actually need to go here and do anything because you either go to the waypoint manager to query it in the first place. And once you acquire a particular point, let's say this one, then you either query for the next node or you trigger the waypoint use once you get it in the first place. And that's basically it. And in the patrol part of the enemy AI, we'll look more into how this system is actually used to get the node and get to the position. I hope you enjoyed this lesson and I'll see you in the next one. Welcome to the communicator system. This system is responsible for propagating knowledge from one AI agent to another. In this particular case, if one tank acquires the target, it will then try to inform others about it. Let's find out how this all works. The communicator is made out of two parts. One of them is the main system that is attached to all AI agents. You can find this system on every AI instance, a child to the main kinematic body because it uses the collision. The other is the signal, which is similar to a projectile, but it travels directly to another AI instance. And when it arrives, it's meant to inform that AI instance that it has a new target. Let's start with the main communicator component. Here we can find the following parts. First, we have the area collision, which will keep track of all other AI agents that are in the vicinity of this one to not be able to communicate faraway distances. Of course, you can change this by changing the collision sphere shape to different sizes, so this particular AI instance will communicate farther away or on shorter ranges. The other two parts are two timers, the clear signal list timer and the communicate timer. The communicate timer is actually triggered so that the communication doesn't happen all the time, but with a 2 seconds delay in between them. And of course, you don't want to send to the same tank the signal twice, so we keep track of a signal list, and at some point we clear it up because the tank that received a signal from us might have lost the target, and it's good to be able to communicate with it again, but at some point later in time. Now let's look at the communicator script and see how this works. First, I want to highlight the following variables. So the signal prefab, which is actually, you can see here, it's the signal that we use as the projectile. This will get instantiated when we need to communicate between different AI instances. We also have the maximum communication number. So basically, once we send the signal out to 3 different other AI instances, we stop this communicator from working. This is to not overpower the system and let the whole map come after us. Next, we have the nearby list, which will be updated by the area collision on body entered and on body left. So this will get updated with more or less AIs that are in our nearby field. The signaled list is a list of tanks that already have received communication from this one. We don't want to send the same thing twice. The current communication is actually a counter that keeps track of how many AI agents have we signaled to, and this will be used to compare to the maximum communication to stop once we reach the limit. And of course, you can change this to communicate to more or less AIs depending of your balancing of the game. In the initialize function, we get the tank object that is the parent of this, and we also will need a target handler. In the restart, we reset basically the communication so that we can communicate to 3 AIs in this case, and also we'll clear the signal list so that we can communicate with the same 3 AIs that we want. So the main functionality is the throw signal, but before we go into this, I want to quickly point out how the nearby list gets updated. So we have the area collision, and in the node here, we have body entered and body exited. So here these two are actually signals that are hooked up with these two functions. And here we get the type of the body that has entered or left. And if it's enemy and it's not in the nearby list already, and of course it's not the same one, so we want to prevent collision to itself because you don't want this tank to issue communications to itself, then we append it to the nearby list. Alternatively, if this tank exited, then we actually remove it from the nearby list. Basically, this is how we get a nearby list working every frame. Throw signal is not actually called by any other script, but by using this timer, which, as I mentioned, is in the onCommunicate timer. This is also a signal that's hooked up through the Godot system. Once this reaches 0, first we need to make sure that we still have a valid target for this particular tank. So in this case, if the target exists and is the instance valid, and then if we have reached the maximum communication number, we need to stop the communicate timer and of course return, and otherwise we haven't reached it yet and we can actually throw a new signal. Now let's look at the throw signal functionality, and here we need to do the following. First, we need to check if the nearby list has some tanks around. So if we don't have anyone around, then we cannot communicate with someone. So we return. Basically this just stops the execution of this function here. Then we have the other enemy, which we will get from the nearby list, and this is actually generated through a random number, so we get a random index number. We also need to check if the other enemy still exists and the instance is still valid, and then if the other enemy doesn't have already the same target, because if it does have the target, then sending a signal to it would be useless. We don't want to have the same enemy signal twice, so we check it in the signaled list. But if the selected enemy passes all of these checks, then this means we can properly issue a new signal. So we increase the current communication number, we append this other enemy to the signal list. Lastly, we create a new signal, and the first two steps are of course instantiate the signal and add it to the root scene node, and then set up the position as well as the rotation of the signal, and lastly trigger the start functionality, which will receive the other enemy and what target the other enemy should receive. The last callback that we need to mention here is on clear signal timeout. This just clears the signal list to be able to inform the enemies that already have been informed by this particular one. The other part of the communicator is the actual signal, and we can check its code right now. And basically here it looks very similar to a projectile. So besides the start, which actually receives the other enemy and the target, we actually wait for is enabled because we don't want to start moving this while it's not at the correct position. We create the direction vector and then we normalize it, and we move this particular object towards the position using the speed and delta. The other part of this is actually calculating the distance between this current signal and the enemy, and if it's below 1, it means that it has reached the intended target, and if it has the function on signal hit, then it will call it. If it's not, then might be a mistake or might have hit something else, but it should not be the case, and then the signal will actually be removed. This happens with this function. There is also one particular case that the signal might handle. So if we send a signal to a particular enemy and that enemy gets destroyed before the signal reaches it. In this case, this won't work anymore. So we need to have also a lifespan that actually is 5 seconds, and it will automatically start. So if the signal either reaches the enemy or has elapsed 5 seconds after its instantiation, then it will get destroyed. And for the signal hit on the enemy, if we go back to the enemy script, then this is the function we are looking at. This was also discussed in the main enemy video, but quickly just a refresh, it gets the target, and if the target is still valid, then it will set the target externally to the target handler. So this new enemy will get informed about this target via the signal. This is it for the communicator. I hope you liked it, and leave a comment here and tell me. See you in the next one. Welcome to the target handler. The target handler is another layer on top of the sensor manager. If you don't know about the sensor manager, I recommend you go check the other video about it. The target handler is a system that hooks up to the signals sent by the sensor manager, keeps track of the current target, and informs other parts of the AI if the target was lost or acquired. Another functionality of the target handler is when a target that was previously acquired has become invisible. That means that maybe it has moved behind an obstacle like a building. In this case, a lose target sequence is started, and if the target is not found, it will be permanently lost. We need two signals, and they will be called when the target has updates. So on target found and on target lost. And they'll both provide what target was found and what target was lost. In the initialize, we have the usual suspects, which are the params given by the key pair value style of initializing. And we hook up to the sensor manager's on target list update. This is the most important part of this one because this will parse the actual list that was received by the sensor manager. We'll also use a callback to the lose target timer. The main point of entry for this script is on target list update when it actually receives the list of targets from the sensor manager. And here what we need to do is, of course, we need to parse this list and get the target that is the closest to this particular enemy instance. So to do this, we actually put up a minimum distance, and this should be quite huge, and the target that has been found so far. Then we parse the new target list, and for each target, we calculate the distance, and if the distance is less than the minimum distance, then the new minimum distance will get this current distance, and the target will be this one. And this assures that even if there is one target far away, since the initial minimum distance is 9999, then this means that it will be picked, but then once this gets updated, then it will go for closer and closer targets. So if you don't have a target, then this means that current target is null, and the minimum distance target is not null. And this is the perfect case scenario because we initialize the current target with this one. We stop the lose target timer, which actually runs all the time while we don't have the target in our sensors. And lastly, we set was target acquired internally to true. This will be used in another part of this script. And the other alternative is when the target gets acquired not through the tank's sensors, but if the tank gets informed by a signal or if the enemy gets hit from far away by the player. And if a target was found, then we emit the signal on target found with the current target. Once we have the target in place, we need to update its visibility at every frame. So this happens in process, and we have here update target visibility. So how do we do this? Well, first we need to make sure that the current target is still valid. So this means that it was not destroyed by some other AI instance. Then we have two variables, is in range and is visible. Is in range is actually true or false based on the range sensor, and the visible is the raycast from the enemy instance to the target. Is visible will be true in this case, but if we actually opt for the enemy to use this line of sight, then is visible will query the sensors for the raycast and it will set to true or false. In some cases, like the tactical tank AI, we don't need this as we just use the range sensor, but for the other two tanks, this will be used. Next, we can use this functionality to check if it's in range and is visible, and if it is in both, then the target is in the far range, otherwise it's false. Note that even if the tank doesn't use the raycast, we can still use visible because it will be set to true here, so we don't have to worry about that. And if the target is in the far range, then we no longer need the last known position, so we just move it minus 500 meters below, and we stop the lose target timer. If it's not in the range, then this means we have to do a lot of other stuff. And if the lose target timer is stopped, then this means that we just lost the target. So first we create the lose target time, and this is where was target acquired internally works, because this time is what gets initialized in the timer lose target. And if the target was acquired internally, this means it might be nearby in almost the sensors of the tank. And if it was externally, it means that it might be further away, for example, from a communicator signal. This lose target externally is a little bigger to give the opportunity of this tank to actually move to the target's position before it actually loses it. This final check is actually, in some cases, for the defensive tank, we disable this functionality. So if it's not disabled, if it's true, then we start the lose target timer with the value that we just initialized. We also update the last known position to the target's last known position. And lastly, we set up the finite state machine's target in fire range, either true or false, based on all of this processing. When lose target finishes, it will emit the signal that the target was lost. So basically, when lose target timer reaches 0, this means that we failed to acquire back the target, and we can call the onTarget lost signal and remove the current target, make it null, and this will actually permanently forget about the target. Other functionalities here are disable lose target and enable lose target, which set up the should lose target to either true or false. These are for the defensive AI, and they are called only when this AI goes into hiding, because it will surely trigger this and we don't want to lose the target after its functionality happens. Basically, this is the target handler. Let me know in the comments what you think about this. Let's look now at the cover system. This is the system that checks the available cover positions for the current tank AI agent, and if queried, it returns a good one. The cover system is made out of two parts: the cover system script, which is found in every AI instance, and the building script, which is found in every building instance. Starting with the cover handler, the main functionality here is get retreat point. It can also receive a parameter of a cover that we want to exclude from our search. Firstly, we need to go through the list of buildings. To do this, we actually need to get the buildings, and they're nicely placed in a Godot group called buildings. And of course, we do require a target, because if you don't have a target, then we don't have a relative position that we can check to get the cover from. Next, we need to set up our strategy, and there are two strategies. The first one is get the closest available cover, and the second one is get the furthest in case of the tactical tank AI, which needs to take a lot of space between it and the player. And based on this, the cover distance is either 9999 or 0, and this will be used to compare with the first pick to make sure that the first pick always gets used. Next, we need to iterate through every single building, and then we query that building to get the best cover, and of course we need to provide the player's position to get the cover from the player, and you also compute the distance from the current enemy to that position, because based on that distance we will adjust our strategy. If no cover was found or the cover was excluded, then we will skip it. If the cover was already used, we will skip it as well, because we don't want to use the same cover multiple times in a sequence. Next, we actually get the cover based on the strategy, and if it's the closest, then this means that the distance between the enemy and the cover needs to be smaller than the found cover distance. And from the step above, we actually set this to a high number, so we make sure that the first position is always received, and then we set up the found cover and we update the cover distance with this. The same thing, but in reverse, happens to the furthest, with one specification, that we also need to make sure that the distance is smaller than the detection range, because otherwise we will enter the search target state instead of actually shooting the player. After all of this parsing of the buildings and covers, if we have found a cover, then we need to initialize last detected cover with it. We also add it to a list of used covers. This will prevent using the cover multiple times in a sequence. Then we compute a position. From the cover's position, we offset it a little on the X and Z axis, just to give it a more dynamic engagement instead of the AI going to the same place twice for the same cover. The add cover to last used function basically adds this cover to a list of used covers, and based on the max number of used covers, we will remove the first one, so we will keep cycling in and out older covers and newer covers. So in this way, we make sure that we can use older covers but not newer ones. And this list is actually specified here. So this is the list of used covers, and we can specify the number of maximum used covers to 7. So we need to use 7 covers before you can use the first one. Of course, you can change this value to make it as you like. Let's now look at the building and see how an actual cover is chosen. So going inside the building and checking its 3D shape, we find out we have this cover element that contains 4 covers, because I just picked the 4 sides of the building. So we have cover 1, 2, 3, and 4, and those are rigid bodies because we need to check the collisions against them, and they have a collision shape which is a box shape. We also have the cover ray, and this ray will actually get moved to the player's position, and it will be adjusted so that it will go through one or a different cover to make sure that it's visible or not from the player's point of view. Let's look now at the code. First, we get the list of all the cover points, so basically get the node cover and get all the children. We also need to disable the collision shape of these, and we will only enable it once we are checking that particular cover position if it's good or not. The main functionality here is get best cover. So first we will use this variable found cover and you'll set it to null. This should be filled with either a good cover or we'll continue with null. Next, the covering needs to change position and it will be changed to the player's current position. Next, we iterate through every single cover. Then we of course need to enable the collision shape. It's kind of redundant because it's disabled false, so basically it's enabled. Then we make the cover array look at the new cover position, and also we force a Raycast update to make sure that this cover array works properly. What this does is basically checks if the array is colliding, and if it is colliding the cover, then this means that the cover is bad. But if it's not colliding the cover, like in this case, that it's probably colliding an obstacle, like let's say a building. So this means that the cover is valid. And once we find the valid cover, we initialize the found cover of it and we break the execution of this for loop. Lastly, we return the found cover so that it can be used by the cover system in the enemy AI. Basically, this is how the cover system works. Of course, it will be used by the retreat functionality and by the attack functionality in the case of the defensive tank AI. Let me know what you think about this system in the comments down below. I'll see you in the next one. Welcome to the Patrol functionality. This consists of two parts: the finite state machine for patrolling and the actual code to make it work. First, let's understand what patrolling does exactly. When this state gets triggered, it will try to make the tank patrol. For this, first it will try to acquire a new waypoint system. If a free one was found, it will be used. If not, it will move to a randomly generated position nearby, with sometimes generating a faraway position to make it more dynamic. This is the first level of the state machine. We need to go down one level more inside the patrol by double-clicking it. Note that the patrol is called when the state machine is started, as this is the default state. Also, this state will be used if there is no target and the AI agent is not currently retreating. The patrol is one of the simplest state machines. It's made of two states: get a position and go to that position. If it has a target, it will exit these states and continue into the attack state. Let's check the code now and see how this works. In the initialize, besides the regular parameters, we will use the tank mover and connect to its finished moving signal. This will be useful to know exactly when to generate a new patrol point. On entry is called when a new substate is entered, and here we need to reset the turret's position. This is the first thing, because it might be rotated from the attack finite state machine. And if you are in the get position state, then we first need to stop the tank mover and then find a new patrol strategy. The find patrol strategy function is divided into two parts: checking for a waypoint and then generating the actual path. We need to check if this AI doesn't currently have one waypoint, because if it does, then we just get the next node and that's it. But if it doesn't have a waypoint, then we need to query the waypoint manager and get the closest available one, if there is one, free. And if it is, then we initialize it and we notify that it's in use so that no other AI agent can use it as well. After we either get a waypoint or we don't get, if we did had a waypoint, then we can generate the move path using the functionality from the Navmesh, from the current position of the AI tank to the current waypoint's position. This will generate a sequence of steps that we can feed into our tank mover. In the case that we don't have a waypoint, then we will generate a random number and you will use those numbers and add it to the current positions X and Z, so that the tank will move slightly around. After the close random position maximum is reached, then the tank will opt for a more faraway position. This will make the tank more dynamic. After this, we will have in pose X and pose Y two different values, and we generate a new patrol point, and then we get the path to that. So when this whole sequence finishes, in move path, we'll either have a move path towards a new waypoint or a move path towards a new randomly generated location. And we put this into the tank mover using start move. If you don't know how the tank mover works, you should check the tank mover video. We also need to set the trigger of the finite state machine so that it will go into the go to position. the difference between a trigger and a value in a finite state machine is the fact that a value is continuously checked while a trigger just gets triggered once, the state transitions immediately, and then that's it. So they work kind of in a similar way, but you have to remember for state variables like hasTarget, for example, to always make sure to be in the right true or false state. Otherwise, you might get wrong transitions. When the new position is reached, unfinished moving will be called by the tank mover, and we will set the trigger back to get position. So basically the state machine will get a position, will issue the tank mover which will move to that position. When the tank mover finishes, it will go back to get position. Basically it will go get position, go to position, and over again until something happens like acquiring target or a retreat functionality. This is the patrol functionality of the AI agent. I hope you enjoyed it. Let me know your feedback in the comment section down below. Let's find out about the retreat functionality, one of the 3 states of our AI agent. The retreat feature consists of a state machine definition and the state code to make it work. It gets triggered when the AI agent's HP drops below a certain value that can be customized for different behaviors. Let's start by looking at our state machine. So this is the first level. We need to double click into retreat, and here you'll find the following 3 states. First, when entered, the retreat functionality will try to find a valid cover. If a cover was found, then it will go there to that cover, and then it will wait for a certain period in the cover. If the cover is invalidated for some reason, for example, the player moves and has a direct line of sight to the enemy, then the cover will get invalidated. It will try to find a new cover. If should retreat is false, then this means that this state is no longer available and the AI can move to attack or patrol state. Let's look now at the code and how everything is put together. After the initialization step of various objects, we also need to connect the tank mover so that we have unfinished moving, but we also have 2 important timers: search for new cover timer and validate cover timer. So what do they do? If you checked the patrol state, you probably are aware that when the patrolling gets called on entry, a new patrol position is picked and the mover is set to go there. The on entry happens only once, when the state machine initially transitions to this. For cover, it's a little different, since the patrol will always get a position no matter what, while this system might return 0 covers, and then the AI will enter in a lock state, waiting indefinitely. To prevent this as much as possible, we will use the callback from the timer search new cover, and this will ask the cover system from time to time to get a new cover, and when found, we will transition to move to cover. If not, we will restart the timer and call again and again, because there is one special case when this situation won't change. If the enemy AI and also the player don't move at all, nothing will change. But usually in real life scenarios, the player will most likely move around and the situation on the battleground will change. So this means that even if the first time we didn't get a cover, chances are we will be getting one the second or the third time. When go to cover state is reached, we know for sure where to go, so we can use on entry to set this to work. Once the position has been reached, the wait state will get triggered, and lastly, here we need another timer called validate timer. So how does the timer search for new cover work? Well, initially on entry happens, we will enter the find cover state, and of course the tank mover needs to stop. And then we actually call the callback function for the timer to just get it started initially. And here in on search for new cover timeout, we will try to get a new cover point from the cover system. If it's different from null, then we set the finite state machine to true so that it advances to move to cover. If not, then we call the timer search for a new cover again in hopes that in a couple of seconds the situation will be different. Right now it's positioned at 1.5 seconds. So it will try to search for new cover every 1.5 seconds. Once we get the cover, we can properly transition to the go to cover state. And here, first we need to set up the finite state machine should wait behind cover to false, and then generate a new move path that we'll give to the tank mover eventually from the current tank position to the cover point. Once this trigger unfinished moving is called, then it means that it should wait behind cover, and basically this is how it enters the final state, wait. And in the wait state, on entry, it starts the validate cover timer. What does the validate cover timer do is once it reaches its timeout, then it will get all the targets in range. And if one target has a direct line of sight to this particular AI instance, then this means that we need a new cover. And of course, we revert the cover point to null and then stop the execution of this here. If not, then we'll be still running in this state and we will restart the timer to validate the cover again and again until something happens. Either it's invalidated or the AI enters a completely different state. And of course, when this state is left, so on leave, if it was in the retreat wait, then the timer validate cover needs to stop. So this is more for deinitializing purposes. And this is the retreat system. First, we search for a cover. If we don't find one, we keep continuing searching for one. Once we do find, we will go to that cover. Then we will wait. If the cover either is invalidated, then we will try to find another one. Or if the state is no longer necessary, we will exit and go to either patrol or attack. I hope you like this system. Leave a comment down below and let me know. Welcome to the attack functionality. Every tank type in this project has a different attack structure. We will need to go through each state machine and also through the code that powers everything. But before, we need to discuss the bigger picture of the attack. Because when an AI agent receives a new target, the attack state is triggered. This happens for all the tanks. Most likely, the target is not in the firing range, so the tank needs to adjust its position to get close to it. Once it's closer, it will fire and then it will do a reload, also known as a cooldown. There are some variations to this as following. The aggressive AI will follow this pattern: move to target, attack, and then reload. After the reload, it will try to move to target if necessary, then attack and reload. The defensive AI will follow this pattern: move to target, attack, burst, cooldown. So this means that a series of repeated attacks, then reload, then go to cover, and then finally repeat. The tactical AI is gonna first move to cover position, then attack, then do a cooldown, and also adjust if necessary. And lastly, move to cover position again. So basically everything has a cycle, but it's a little different. So we'll go into each state machine and see how it works. Let's start by looking at the script that powers everything. After the main initialization of various objects and systems that are required for this, we need to look at some other objects that are really important here. And some of these are, of course, the timers, because we already know the tank mover is the system that is responsible for moving the tank and that sends a signal on finished moving. But we have a couple of different timers like reload, burst, cooldown, go to target. So let's quickly go through each one of them and see what they do. The reload timer is triggered after each shot to put a delay between them. The burst timer is used for the defensive AI to fire a sequence of projectiles and then do the reload. The go to target timer is triggered when the location was reached and the AI needs to wait a little, let's say idle time, to make it look more realistic. The timer target search for how long the AI will actually search for a lost target, and the cover wait will know for how long the AI needs to stay behind a cover. We also will adjust some default parameters for the finite state machine. In on entry, that happens only once the state enters, we have the following things. If it's the entry state, then this means that the state for the attack was the initial one, basically the entry state here. And only if it's the entry state, we restart the communicator. And if it's any other state, we'll do the following. If the tank is in the go-to state, we first need to make sure that the target is still valid, because we cannot go to a target that's destroyed by another enemy. We will generate a new path towards it by using the Navmesh and get simple path. So we will stop the tank mover in its current path and we will send the new path, the move path. This state will exit once the range between the AI agent and the player gets lower than the firing range of the current AI. This range is updated at every frame. We will look at that into a second. Once we are entering the firing state or the attack fire, we need to check the target to see if it's still valid. We will stop the tank mover because the next step is to fire a projectile. So we will issue a fire command. If the state is go to wait, we will start the wait timer. We will of course stop the tank movement and then start the go to timer with a random range to make the tank look like it's holding its breath for a second before continuing to a different position. The next state is called search for target state. And here the first thing we do, we need to set the is target search over to false. Then start the target search timer. This timer, once it reaches 0, it means that we didn't find the target in the timer. So it will completely remove the target from this AI's memory. And lastly, we need to stop the tank mover and we will need to generate a path from the current position to the last known position of the target. And we will give this path back to the tank mover. Of course, we need to set up the parameters for the final state machine that is target search over to false because we are just starting it. The hide state is specific to the defensive AI and is called after each reload happens. The tank will do a sequence of fire, then move to cover, then fire again. For this, we need to stop the tank mover. We need to get a new cover point. And of course, if the cover point is not null, so this means that it exists, we need to generate a new move path using the Navmesh, give this to the tank mover. We also need to disable the lose target from the target handler. This will make sure that once the defensive AI breaks visual contact to the target, we don't actually start the lose target timer because otherwise it will go into hiding and then it will lose the target by the time it comes back. And we need to initialize the current cover to the last detected cover. We will also set up the cover miscount to 0. The attack adjust position state is only used for the tactical tank AI. This state, what it does is basically detects when the tactical tank AI doesn't hit the player over and over again, which means that probably it's quite close to a building and we need to adjust the position. So first, of course, we need to check if the target is not null. Then we need to stop any movement. We'll calculate a direction vector from the current AI agent to the player. And basically we need to move in the opposite side to get a clearance between the AI agent and the building. I just put -10 here. So we'll get the current tank position. We add the new direction that we just calculated between it and the player. And we multiply this direction to -10. So we get a proper clearance, hopefully. And then we'll move to this new position in hopes that the adjusted position will be better from the current one. In on-update, things happen every single frame when this state runs. If there is a target and it's valid, we need to look at it all the time with our turret. Of course, you need to set other 2 rotations of the turret to 0 so that the turret doesn't tilt in wrong ways. And then we will also need to check the distance between the current AI agent and the target to see if it's less than the attack range. And if it is, then it is in the minimum range. And this will be used for firing purposes. On update, also the tank turret position animation happens. And basically what this means is we set up the position based on the tank turret position, which is a position 3D on the tank body. And we need to move on the forward axis using the turret anim forward, which is basically a float value from 0 to 1 that is animated real time when a projectile gets shot. And also on update, if we are currently searching for the target and the tank mover has finished its path, we don't need to wait. We need to move the tank around to see if we can find the target. So for this, we will generate 2 values that we can add to the current tank position so that the tank can move to nearby locations and see if it finds the target. Of course, if no target is found, then eventually the target is permanently lost. Now we are entering the fire function. And in here, we of course need to instantiate the projectile. We will also play the animation. So first we reset the animation and then we play the turret fire. And there are 2 types of attacks. The regular one is just firing projectile and then entering the cooldown or reload. And the second one, we will fire multiple projectiles in a burst. And then after the maximum burst projectiles was reached, then we enter reload. If not, we start the burst. The burst is basically just a smaller reload, so it acts the same, but instead of having a longer wait times, so we fire a series of 4 projectiles one by one and then have a longer time to reload all of them, and then we fire more. The burst is used for the defensive tank AI because the turret there has more locations that it can fire projectiles from. The reload and the burst functionalities are very straightforward, so first we need to set easy loading to true, and in the case of burst is burst cooling down true. Then we we start either the reload timer or the burst timer cooldowns, and both of them actually are randomized between different ranges. This will give slightly different variations of the cooldowns to make it look more realistic. And lastly, we set the finite state machine to is reloading or is burst cooling down. This will make sure that the finite state machine is in the correct state. In the instantiate projectile, which is called here in the far, we need to create a new projectile, and we will use a new instance of the projectile prefab, which is a scene in Godot, and we will add this to the root node of the scene. The next step is, of course, to get the fire point, and the tank can have one or more fire points depending on its structure. This code will cycle through multiple target points. In the case it's only one, then it will just give the same one over and over again. If not, it will give the next one and then the next one, and then it will go back again to the 0. We also initialize two visual effects, the smoke and the muzzle, for each projectile shot. And lastly, we will initialize the projectile. And this is the interesting part, because we have 3 projectiles and each behaves completely different from the previous one. And some might need some parameters, others might need different ones. I opted to include all the parameters for every single projectile. And this is because by doing this, even though some projectiles once initialized will receive parameters that they don't use, we can use one initialized line, and then we can swap the projectiles here to whatever we need. And we don't need to have 3 different initialize sequences like this, like 1, 2, 3, of course, with ifs between, and check the projectile type, because all of them share the same header. So this is quite cool, and this is very maintainable for a project. And this part of the script handles a lot of callbacks from various systems and timers. So for example, onFinished moving is actually called by the tank mover, and it will start the cover wait timer if that's the case. And if it's the tactical enemy type, then we'll set the should adjust position to false. On projectile miss is actually called by the projectile, and this is mostly used for the tactical tank AI to adjust its position. And this one needs to know if the current hit object was actually the terrain and not the building. Because if it's the terrain, then we won't continue, because it's not actually a miss. We only go through here if the object was a building or another object that was between the enemy and the tank AI. We will start increasing the miss count, because if we reach the maximum miss count, then we will set the finite state machine to adjust the position. We will also use the cover miss count. So this next step is that even if we try to adjust the position locally in the same cover for, let's say, 3 times, if the cover is still bad, then we need to change the cover entirely. So we count this cover miss count, and if this one gets reached, then of course we set it to 0, because we need to make sure that it works again and again. But we will stop the should adjust position, and we will call is cover bad, and this will actually trigger a change of cover to hopefully a better one that can actually reach the player. onFinished reloading is actually gonna set the is reloading to false, and then depending of the enemy type, it will either do the reloading for the aggressive and tactical AI, but for the defensive it will trigger the attack hide, because after each single reload, the defensive AI will go into hiding. On burst cooldown finished, we need to set the burst cooldown parameter to false, and then we need to inform the finite state machine by setting the parameter as well to the correct one. On go to target finished is basically called by the timer when we already have some wait time and the current new target, and we need to stop that wait time. On is target search over is called when the timer for the target search has timeout to 0. And lastly, on the cover timeout is called when the cover wait timer gets 0, and we need to call the trigger for the finite state machine. Also, we need to set the target handler to enable lose target again. Now let's check each individual state machine based on the tank, and I'll start with the aggressive one. In here it might look like it's a mess, but it's actually a calculated mess. One entry happens when we actually acquire the target, and on this branch should retreat is false, because we don't want the enemy AI to retreat. The go to functionality will generate a path towards the target, and we'll try to move the AI there. And if the target is in range, then we will trigger the attack fire, and after the attack fire, if everything is fine, so this means that it still has the target, it shouldn't retreat, then it will go to attack cooldown. Of course, the parameters here need to be that it is reloading, the target is still in range, and it's not retreating. And once the cooldown finishes, it will set the parameter is reloading to false, and it will enter the fire state again. And basically, if it is in range, these two states will bounce back and forth until the enemy AI kills the player. In the case that the target is not in the firing range anymore, and this is false, it will go to wait, and it will wait some time, and then it will trigger go to the target. At some point, this or this might actually go to the target, but might lose the target. And in this case, the has target will be false. And in this state, attack search target will enter. And here the AI will go to the last known position of the target, and then it will randomly search around to see if a target was found. If the target is found, then this will be true and it will go back to go to if it's needed. And if the target is in range, it will go directly to the fire. And if search target state finishes with no target in sight, then the search is over and we exit this state, probably heading over to patrol state. And this is the finite state machine for the aggressive AI. Now let's look at the defensive one. So the defensive AI has a similar state machine because it still enters, it still goes to the target. If the target in range, it starts to fire, but the fire sequence first will bounce between fire and burst cooldown. This will happen for as many projectiles we can launch per session. And once the session is over, we'll go into the cooldown. After the cooldown is finished, instead of going directly back to fire, we'll go into hiding. So this means it will pick a cover point and will try to go there. Once a certain time passes, we will end the hiding and go to the target again. And once the target is in range, go to fire, then the burst cooldown, then fire again, cooldown, hide, go to, and it will go to this loop until eventually the target that might be lost or might be in search target mode. So this is the defensive enemy. And lastly, we have the tactical enemy, and this one has the most different state machine because once it enters, it will actually go into hiding, and hiding in this case, it will pick a cover point that is relatively far away from the player, and after it's safe, then it will trigger the fire. In firing mode, of course, you'll go to cooldown, and once the cooldown is finished, the fire mode can also detect that the projectiles haven't hit the player for a while, so this means that we might have a building that might actually interfere between our shots, and in this case, the adjust position is called. The adjust position basically creates first a vector between the enemy and the player, and then moves in the opposite direction so that it will give the enemy AI a bigger clearance from the building. If after a couple of adjustments of the position, the fire still hits the building, then it will try to change the cover. So it will go through is cover bad true, and then it will swap location. This means that the cover will be swapped for hopefully a bad run. And here it doesn't happen anything. This is just a small transition state because the cover will still use the same functionality from attack hide. And then it will go back to fire and go to cooldown and then check if the position is to be adjusted or not and do this back and forth. Once the target is lost, we will enter the search target state, which is similar to the other two enemy types. And if the target was found, of course, we need to go back to cover and then start the fire sequence. But if the target was not found, then we will head over to exit and probably go to the patrol state. We shouldn't worry about the tactical AI because this one has a huge range, so most likely it will get the target back again. Also, one difference from the other two AIs is that this AI doesn't require the direct line of sight. It will be much more likely to find the player than the other two. And basically, these are all the state machines for the three enemy types. I hope you like them. Let me know in the comment section down below.
Welcome to the quick introduction to programming. If you are a beginner, then definitely don't skip this. Since we will be using code to implement various systems, it's always a good idea to get up to speed. All of the code will be in GDScript, Godot's native scripting language. Let's look at the core building blocks and how to use them to create more complex functionality. First, I want to mention that all of these examples are available in the downloadable project in the course. If we look at the variables scene, we have the script. By the way, we will discuss first about variables. Variables are used as data containers. They can store numbers, strings, and even more complex things as objects, materials, and whatever the developer needs. They do come in more shapes and sizes. Usually, when creating a new variable, it can store only one thing at a time. This is good for values like hit points, damage, speed, etc. When we are discussing about variables, a core concept is called variable declaration, and that one means to let the engine know that we are creating a new variable. The declaration goes like this: var, which is an operator, and then the name of the variable. That can be whatever you like. I'll just keep it a. So by doing this, var a, I'm actually specifying that, hey, I want a variable called a from now on. So I cannot use it before this. We can also initialize the variable when we declare it by putting an equal and then putting a number, a string, or an object. To display the variable in the console, we can use a handy function called print, and then in its parentheses, as a parameter, we can specify a in this case. We can try it by pressing F6, and of course, we will get 5, because that's the value contained in the variable a. Now let's look at the string, and the string is very similar. You can see we can just call it string. By the way, we can specify the type of a variable by adding colons to it. So if I say string, then this variable will be string. Why is this important? Because if we want to assign later another type, then we will get an error because only string is available for this one. Keep in mind that if we don't put this, then we can assign whatever we want, but this will create confusion later in the code. A float variable means a number that has decimal points. For example, pi, which is 3.1415, and so on and so forth. When we need a list of elements, let's say a list of words, we can use lists. Lists or arrays are also variables. The main difference between them is the fact that they can store multiple values chained one after another. They are good to store groups of items like inventories, enemies, projectiles. To create an array, we can declare it as a regular variable and then just use these brackets and we have an array. We can also initialize the array as it's here with different values separated through commas. Keep in mind that to reference a particular value in this array, we can just say array, and then in the same brackets, we can just specify the index starting from 0, which would be 1 in this case, 1 and 2, which will be 3. So this is 0, 1, 2. We can also get the size of an array by calling array.size, and this will return 3. The array also can be parsed, but that is for later on. Another type is also vector2, which is a Godot type, and vector2 stores a pair of values, x and y. We can define it like this, and to call it, we just say vec, because that's the name of the variable, and then x or vec.y. Of course, there is vector3 and more. You can find all of the types supported by the GDScript in the link down below. Now let's look at operators. With variables alone, we cannot do much, not even store data, in fact. Not because they cannot, but because we need to use an operator to actually assign a value to a variable. Now let's look at the code here and let's assign two values to two variables and then use the addition operator to add these two values and assign the new value in a third variable. So first we have a, which is 1 because it is an operator assign. Then we have b, and then we have c, which is the sum of a plus b. So the order of the execution of this is of course a plus b, and then the final result gets assigned to c. You can print c, so you can see that the number will be 3 in this case. There are other operators that you should know of: addition, subtraction, multiplication, and division. All of these operators work exactly like in math, with the observation that the division cannot be divided by 0. It will result in an error. Not all of the operators handle calculations. For example, we have the logical operators and or. What they do is basically they handle a unique variable type called Boolean, which can be either true or false, as following. For example, if you use the AND operator, it can also be as this symbol. If we have true and true, it will be true. If we have true and false, false. And false and false, it will be false. For example, this is good in conditions like, is the AI moving to a particular target, and also is the AI having a particular health? Then it's true. Then otherwise it's false. And the OR operator is a little different, of course, because true and true equals true, but true or false equals true. So the difference is that only one of the conditions need to be true in order for the whole statement to be true. We can put it to the test and see the result. Of course, this is AND, so true and false will be equal false. And this is how we can actually use them. Let's say we have a variable called is enemy visible and true. And then in the next section, when we will be discussing about flow control, we'll see how to get the most out of these operators. Now that we can store data and manipulate values, we need to discuss about code execution. And the code executes from top to bottom without stopping. Of course, an algorithm cannot be created just by lines of code written without any flow control. This is why in this section we will be discussing about flow control instructions. And they are very important because otherwise nothing will be possible with programming. So let's find out some flow control instructions. Firstly, we need to discuss the if instruction because this one is the most common. And if is very simple. You just use the operator if and then a statement that needs to resolve in either true or false. In this case, I'm using the operator double equals, which actually compares, it doesn't assign, it compares the value from A with 1. And since this is actually true, this will return true. So in this case, if will go through the first section, which will execute this part of the code. If A wasn't equal with 1, then it would have went to the else branch and it would execute that part of the code. Keep in mind that the else branch is optional, so it can be completely removed if not necessary. For example, a code can be just if A equals 1, do something. If not, then I don't care about that part of the code. Now let's look at another important function, which is similar with if, but has something particular. This one is called the match instruction. And in other programming languages, you might be familiar with the instruction switch because it's very similar. So the main difference between an if statement and a match statement is the fact that in an if statement we can have a statement made out of multiple instructions, while here in match we have a variable, let's say A, and then if that variable has multiple numbers or strings that can be, then it's much easily to write this. Keep in mind that with if we can actually implement a match instruction, but with a match we cannot really implement a complete if instruction. In some cases, for example in this one we can, but in some others we cannot. Let's quickly look at how we can implement this match with an if. So if A equals 1, then print is 1. And then there is another instruction called else if. It's basically else and if combined, and A equals 2, print is 2. We could have opted for this implementation, but as you can see, if we add more values here, like 3, 4, etc., then the match is much more pleasant for the eye to parse rather than using an if statement. So you might be considering what to use based on what values you are comparing. While the if instruction and the match instruction actually branch out the code, we have other types of flow control which actually deal with looping code. And the most common one is the for instruction. And the for instruction works like this. We have a value and we can give it a range, a list, and some other things to iterate. Also, the for might be called the iteration operator, because what it does, it goes through a list of values and parses each one of them. So if we would to run this, it will print 0, 1, 2, 3, 4. Let's see. So for the for instruction, we have 0, 1, 2, 3, 4, because it starts from 0 and of course needs to be lower than 5 to actually finish. One pro of the for instruction is the fact that we can iterate lists like the one described in the previous example, and also ranges. So for example, counting and so on and so forth. One disadvantage for the for instruction is the fact that we cannot parse values that we cannot count. And for this, we can use the while instruction. The while and for are very similar in a lot of cases because they both loop code. They both work in similar ways because they test the condition to loop another time. But one major difference is the fact that the for knows exactly how many steps it needs to take and the while doesn't. In this example, we can clearly see what that means. For example, we have the HP of the player and then we will subtract different values, in fact random values from that HP until it reaches 0. This might be, for example, while health is more than 0, but we don't know exactly how much, because in this range we actually subtract from 10 to 30 points. And then by just running this, we can see that sometimes this happens with less steps and some other times with more steps. Let's quickly try it. So I'm going to press F6. So in this case, we started with 100 and then the health decreased and then we ended up with 7 steps. Let's run it again. Now it seems that the random did a better job. So we ended up with 6 steps. This could not have been implemented with a for. Now let's look at functions. Once you start writing code, you will find out that parts of the code repeat themselves. And this is normal in programming. In fact, it's the way it happens. When you find these patterns, you can make them reusable by creating a function. A function is a separate piece of code that can be called on demand by specifying its name in the execution. Let's look at the code. So here we have defined a function add. To create a new function, we need to use the operator func in GDScript and then the name of the function. And we do need to use the parentheses, but they can be empty or we can specify additional parameters. Don't forget to add the columns after each function implementation. In the function body, we can do something with the provided values. And in this case, we just add them and we used another operator called return, which will return the final value. And this value can be used in the previous function that called this one. In this case, I'll be saying adding 1 plus 1 and then calling this function. This will add these two elements and will give the result to be printed in the console. Keep in mind that now we can use this add as many times as we like to add two values. But this can be a move function. This can be a fire projectile function. This can be whatever you want. There is also another type of function called recursive function. And the recursive function is just like a regular function with the one spin that it calls itself in its own body. As you might imagine, if you see in the Inception movie, this can lead to infinite execution and we don't want that. So remember, if you ever implement a recursive function, then you need to make sure that you have something called the exit condition. So the exit condition is usually an if statement that checks a final condition to break this recursive pattern. This is important to prevent the function running indefinitely. Recursive functions are useful in some particular algorithm implementations in this course. Welcome to the data structures bonus section. In this module, we will look at various data structures that are useful in game AI algorithms. In order to implement game AI, we need to store information, and we do this by using variables or lists. But for the algorithms, sensors, pathfinding, and other things that are required for game AI algorithms, Well, we need more data structures. Let's look at some other options that are out there and how can we use them. Let's start by looking at the queue. The queue is very similar to a list. That means that it does contain data stored in an array-like format, similar to a list. It's an abstract type, which means that it doesn't have a specific implementation, but in most game engines and in most languages, it's already implemented in a way or another. The main difference from a list is the fact that the elements in the queue get added only at the end of it, as here, and they are removed only from the beginning of it, as here. And this is very similar to a cinema queue in real life. Now let's look at the implementation of the queue in GDScript. Here we have a queue, which is basically a list in Godot, and we can use the append function, which is the same as for a regular array, and the result is, of course, 1, 1, 2, 1, 2, 3. Append actually appends at the end of the list, so it's really good for us. If we print this out, then this will be the answer. And as I mentioned, we only need to remove elements from the beginning. In order to do this, we can use only this function called popFront, which will give us the first element, in this case is 1, and the queue will remain with just 2 and 3. The queue is very valuable in algorithms for pathfinding, but not only. Let's now look at the graph. It is also an abstract data structure. That means it doesn't have a strict implementation. The user can implement it as they see fit, but a graph's main feature is its nodes, which can store data as data containers, and they can be linked together with edges. Of course, if we arrange them in a grid shape and we put edges between all the neighbors, we end up with a grid-like shape. So basically a grid is just a specific case of a graph. Please keep that in mind because we use also grids in this course. So how can we implement graphs? Well, there are actually a couple of different ways. This first implementation, while it is simple, I don't think it's really that much used, maybe in some particular cases, but it's really easy to understand. So just imagine that each node has a specific ID. In this case, it's 1, 2, 3, 4, 5. And we have a matrix or 2D array that has indices for each row and column. And if we take a pair, let's say 1 and 2, if the value here is 1, that means that there is an edge between them. And if it's 0, then it means it's not. So with the same logic, then of course this diagonal is 1, 1, 1 because it's for the same element. But then for 1, 2, 1, 3, 1, 4, and 5, we have the relationships. So basically only 1 and 2 has it. Please note that also if we cut this diagonal, all of these values are mirrored. And this is because this graph can work in both directions. So for example, from 1 I can go to 2, but from 2 I can go to 1. So if I query instead from 2 to 1, it's also 1. So this is the first graph implementation. Let's look how this can be made in code. And for this, I use a particular functionality called Array2D. Please note that Godot by default doesn't support 2D arrays. So this is actually from a library called Go.next. You can find it by quickly searching on Google. And the first thing, of course, is to create a variable called grid. Then to give it a size, which in this case is 6 by 6. These two fors are just to set everything to 0, and this is just to make sure that everything is clean. And then we can set up the relationships between them. So from 1 to 2 we have 1, from 2 to 1 we have 1 as well. And if we move down for each pair of nodes, we have the edges. So basically this is how we can implement a graph using this kind of structure. Now, one common issue is, okay, we have a graph, but we need to actually go from element to element. And how can we do this? There are a couple of ways how we can implement this. And the most common ones are breadth first search and depth first search. And in fact, these are also used for pathfinding algorithms. In the example in this session, we will discuss the depth first search. But if you check the section anatomy of a Pathfinder, we will discuss the breadth first search as well. So make sure to check that. But how is the depth first search implemented? It's a recursive function. If you don't know what a recursive function, it's in the previous module. Quickly, just to sum it up, it's a function that calls itself. So that's one point. And the other, it needs an exit condition. That means a way for the function to actually not call itself to infinity. And we do this by using something called wasNodeVisited. So we will use a secondary array that will store the IDs of the nodes that were already parsed. So how does this parsing work? Basically, we have a function, let's say parse graph. It receives a node ID, let's say 1. It prints that node ID, and then it puts the node ID in the list, in the visited list. And then for all the other IDs, and we remember that in the previous one, the grid was of length 6. So in this case, for every possible neighbor, we can check if the cell from the current node to the other value is different than 0, then this means there is a connection between them. But of course, I here and current node might be the same node. So they're always 1. So we need to make sure that is out of the question. But luckily we have this. So this node needs to not be visited already. Let's say if it's the same node, so it's 1, then this would be false because it's already visited. This also works, for example, we are in 1 and then we move to 2 and then we go back. We cannot actually go back because 1 was already visited. If we are here, so okay, we are in 1 and we find out that the next node available is 2, then we call this for 2. I actually have an example, so don't worry about not understanding this code properly. Basically, it runs until there is no other neighbor for it. Let's find out exactly how it works in an example. So here we have a little different graph. I want to run the algorithm with you starting from the first point. A depth first search would go first in the depth of the graph, hence the name depth, and then go back when it's no longer possible to go forward, and then try another path. And in the end, go to the first node and finish the algorithm. So let's start. 1, the first node available is 2, as noted here. Then we have 3, and then as I mentioned, the next one is in depth, so it would be 6, not 4. So it's 6. Then this node has no other neighbors, so that means that the parsing here is finished. And then we move back to 3. It's also noted here, but with red. 3 is also finished because it doesn't have any other neighbor. It goes to 2. 2 has another neighbor, so it goes to 4, then 7, then 8. Then it goes back to 7, goes back to 4. 4 still has one more neighbor, 5, 9. So these are the actual nodes that get parsed. And then going back 5 again, 4, 2, 1, and the algorithm finishes. So what we will see on the screen are these numbers with the red ones missing. Basically, this is a graph traversal using DFS. BFS works a little differently because it will parse 1, 2, and then 3, 4, 5, and then 6, 7, 8. So you see, it's more like a spread instead of going in depth first. Okay, now let's move on with the different implementation for the graph. And this is implementing via classes. So basically that means to have another object of a structure that has the list of its neighbors included. And then we can have multiple nodes that specify their own neighbors instead of a matrix that actually contains all of this. This is actually more useful in a lot of real cases. For example, in case of intersections in a city or other cases where we need more flexibility. Because with the matrix, we are kind of dependent on the size, but with this one, we actually use all the possible elements. One special case for the graph is called directed graph. And this means that once we go from 1 to 2 in this case, we can no longer go back to 1 because while 1 does have a connection to 2, 2 does not have a connection to 1. If we were to implement this with the array2d method, then that would mean that we have a connection from 1 to 2, it would be 1, but from 2 to 1 it would be 0. And with the neighbor method, we would have probably an object with the ID being 1, one of its neighbors being 2, and then the object with the ID 2 that doesn't have the neighbor 1 but has the neighbor 3 and 4. This is it with the common data structures in game AI algorithms. Of course, There might be others, but these are the most common ones.